This morning we are going to have 5 talks before the coffee break, and I believe 4 will be in person, 1 will be remote, and each speaker again will have 12 minutes speaking time, and I'll do my best to keep people on track. And so we'll start with Iossif Papadakis. Please go ahead.
Yes, okay. Hello, good morning. My name is Iossif Papadakis. I guess most of you don't know me because I joined AGN Reverberation just a few months ago. I'm local at the University of Crete. I'm going to present work that I did with an embassy student of mine a couple of years ago. The Nuclei language. The work is published, and the Nuclei working again as a student. And I'm going to talk about the timelines in Quasars. I'm going, and here's the list of collaborators in this work. And I'll start with a general statement about the so-called efficient disk size curve. I would like to stress that there is no such thing, right? Okay. What is there is a problem of a particular model for X-ray illumination of the disk to fit the data. The idea of X-ray illumination and standard proportionality disk, as I will show you, is fine. There is nothing wrong with that. It's the way that you try to model, right, okay, X-ray illumination of the efficient disk. That's where the problem comes in, because particular model, and I'll show you here, you've seen this. I think you've seen this one a couple of times here in this booklet. So yes, here are the timelines as a function of the wavelength. And there is this slope. Slope is usually 4/3. And there is this normalization in the model, right? Okay, here's the normalization of the model. Normalization depends on black hole mass, fine, on the accretion rate, fine. But where is X-ray luminosity here? Where is the height of the parameter? Look at this. You've got your X-ray source. Don't you think that the height, will affect your timelines? Don't you think that the X-ray luminosity will affect your timelines? There is nothing here, right? And that's because there's a very basic assumption of the model. And the basic assumption at each disk radius, the X-ray luminosity is equal to the power that's generated by the disk. That is a very, very important assumption, a very simple one. Why would that happen? That depends on the X-ray luminosity and the height of your source. So by forcing that, then you have problems in trying to get the data. And also there are also other assumptions, like the disk reflects like a neutral reflector, right? That there is no ionization, which again is very simple. Oh, it's important to know how much of the X-rays are reflected, because that's the only way to compute how much of the X-rays are absorbed and increase the temperature of the disk, right? Okay. And there is also the assumption that each wavelength is emitted by a single radius. No, that's not true. It's a whole range of these radii that emit P-band, B-bands, Q-B-bands, right? Okay. So all these simple assumptions, can lead to erroneous results when you fit them to the data. So what we did the last few years is that we tried to restudy this problem, right? Okay, by taking into account as much as we could all these subtleties and all these difficulties. Here's a paper, it's almost 5 years ago, right, where we describe our work. And here is a new navigation that's 5 years old, right? This is the timeline of this wavelength, lambda, minus the timeline that you reference back, and that depends on the hash. That depends, of course, on your black hole mass. It depends on your accretion rate, but also it depends on the X-rays. It also depends on this spectral hardening factor that many people use when they model, their SEDs. Because you have a black body, but of course this black body will be modified by scattering effects on the disk atmosphere, and lots of people use this hardening factor, right? Okay, to correct their spectra, and all these functions of height, of M dot, and of the X-ray luminosity. Oh, and of course it depends on the spin, right? There was no spin in the previous equation, and these functions are given for 2 black hole spins. At that time, we didn't believe that we could actually, estimate spin. We were wrong, but anyway, and they are in these papers. The energy takes, into account all GR and spatial relativity effects, and these are also important. And it also conserves energy, which again is a very, very important thing. And the model fits the data very, very, very well. There is no disk size problem. here are the data for a few galaxies. This is Iossif 5548, the one that was, supposed to be the problem. No, you can fit it very, very well for reasonable parameters. But indeed, VLR is there. Actually, when we were fitting this, we were not taking into account the U-band data, right? Okay, the VLR is there. All what we were trying to do is that the general size of the time lags, yes, they can be explained by X-ray illumination of the standard separation line, not stone in this case, because we have spins that are up to 1, right? Okay. And here is this is a paper that we just published, right, with a student of mine. This is the famous 5548 data. We fitted every single observation, so we now know X-ray luminosity, and we actually predict the UV data. By the way, everything here is in physical units. We actually predict the UV, and as you can see, predictions are fine. This was the object where people thought, oh, well, X-rays are not very well correlated with UV. They don't have to. The basic, prediction of the model is that the UV and optical will be almost identical, not the X-rays with optical UV. That's not the case. So here we drive physically with the proper luminosity, everything that you observe, everything's fine, right? Okay. There is no accretion disk size problem. It all depends on the modeling. But now, and by the way, we can fit the luminosities, we can fit the optical power spectra. There will be a couple of papers that will appear very, very soon. Parallel 9 and Iossif 4151. We have already done that for 5548. And I'm going to show you now that this one works also for distant quasars. So what we did is we got time-lapse measurement from these papers. These papers, they use ETF light curves, they compute GI time-lapse. This paper, uses SDSS light curves. This one uses Quasars light curves. In total, we have 128 quasars. Here's the distribution of the properties in our sample. We've got quasars. We had to put a cut at high black hole masses and high accretion rates. I explained that with time why we did that. Here's the volumetric luminosity, and here is a range of redshift in our sources. These are not nearby secrets like the other ones. And here is a plot of the observed time lags. Now, here, what I do is the following. I plot here the rest frame wavelength of the secondary light curve that we use to compute light curve, the time lag, the reference band. In all cases, the reference band was G observed. But of course, rest frame G is different to each source depending on the redshift, right? And that's why you have this range on the x-axis. The secondary band, although it is I, R, Z, it's not the same, the rest frame, because of redshift. But there is also a very large, range in time lags because time lags still depend on black hole mass, accretion rates, and X-ray luminosity. And the sources have different black hole masses, different accretion rates, different X-ray luminosities. So what we did is we computed average time lags in these rest frame wavelengths. And what we did was the following. We used the estimation of the black hole mass that is there in the paper. We used the estimation of the accretion rate of each source. And then we tried to estimate the X-ray luminosity. And to do that, of course, we don't have information, but we used published relations. In this particular case, we use the Cosmos Lusso et al. 2012 relation between the 2 to 10 keV luminosity and the Heraklion ratio and the volumetric luminosity. And then we can fit the data with 2 free parameters, height and, of course, the spectral hardening factor. That's it. Since you have all the other physical parameters, all you are left with, for these different black hole spins. And you fit the data very, very well. This is our fit for the 0 and 1. The case of black hole spin 0, the hardening factor is 1.7, which is very, very normal. And the corona height has to be between 20 and 70 Rg. And in fact, when now you go to individual sources, these are the predictions for each individual source. These are the residuals. And when you plot the residuals, indeed, they are very well, the residuals are very well fitted by a Gaussian, so the errors are random, around 0, and with the width which is equal to the mean error of each time lag measurement. So everything is fine, right? Okay. So this is the takeaway message. X-ray illumination of standard Novic orthotics can work. It can actually give you good fits to the time lags, and it can, whether this is a nearby secret or this one is on. We can also, explain the luminosity, the optical UV power spectra and cross spectra as well. Different story. Oh, and this is very important. Look at this. And that was the biggest problem, I believe, of this, which came from this multi-wavelength Swift circuit. Look at this is the HST 1158 angstrom light curve. Look at this. It goes from 10 to 25. This is physical units. So this is a factor of 2 increase in flux in 15 days. Now, a normal accretion disk cannot do that, no matter what is the time scale. So that was the biggest problem with these observations. The AGN appeared to be very, very variable on very short time scales. But of course, if you now assume X-ray illumination, it's the X-rays that drive the optical UV variability. On these time scales, I do believe the accretion disk is variable, but on the normal time scales, thermal or viscous time scale. But on these very short time scales, the observations that we see are driven by X-ray reverberation, right? Okay, and as I say, we have shown that this can work. And I'll finish, and I believe the best way to try and fit data is not to use existing models, but actually go out there, do your disk response function like the colleagues from Warsaw are doing. Do the response of the BLR, because the BLR is there. And in fact, I believe LSST will give us a fantastic opportunity to actually now try and see how much the BLR contributes to the continuum. And, we can do these kind of things when we have the disk responses and the response of the BLR. Now, we have out there a code, it's free. I mean, everybody can use that one. This code can give the disk transfer function, not in arbitrary units, in physical units, as long as you give black hole mass, black hole spin, the F call, right, the height of the corona, the X-ray luminosity, including, of course, the slope of your X-rays and the E cut in your X-ray energy spectrum, and for any inclination angle. The code is there, and anybody can use it to get these responses and then compare this with the data. And of course, the code includes all relativistic effects, and also it gives you the ability to choose how is your corona powered. Is it powered by the accretion process? So do you steal energy from your accretion and you give it to the corona with an anode mechanism? Or is the corona powered by an external source? Because the time lags are different in these two cases, but you can do it with this code. And with this, I'm going to stop here. Thank you so much for being actually here. I know it's very difficult. It has been a conference dinner. I'm very, very glad to be here. Thank you so much. So thank you.
I can understand why you wouldn't want to consider accretion rates above, I think you mentioned one, but why black hole masses greater than 9 or something?
Because this model that we used this analytical model back then, and this was created. This was based on lots of disk responses that we have created that for black masses out into the night. We never thought we would actually observe objects with larger black hole mass or with larger accretion rate. And there's also an issue here. There's a question: do not solid disks exist when accretion rate is above editor? I mean, at some point one has to think, yeah, you've got a model, but there is physics here, and I'm not sure that. I suspect there will be a limitation up to which accretion rate you use this. We're about to publish a paper on Material 110, I think, where the accretion rate is supposed to be 2 or 3 editor, and we still find very good agreement, but one has to think about it.
do you result botanical strain on the spins for quasars, for instance, or that?
Well, no,
They're
because
present.
that point we could get good fit, but spin matters. But in this case, and with these error bars, sorry, we cannot miss. These are the two spins. Spin matters because one, you've got of course this close to horizon, but also efficiency changes, and that sets the temperature of your disk, right? Okay, so that's why it is important. But in general, with a higher spin, you get smaller timelines. But no, we couldn't with this data. We could not say it's 0 or 1. We could.
Okay, we have time for one final last question.
Thank you for the talk. You know which is contributing more to the heating in this case? Is it the harder X-rays or the softer ones? Like when
It's
you
all X-ray. You have to take the full. So the crucial thing is, where does your X-ray spectrum start from? The E0. And to get that, you have to get all your photos from the disk arriving to the corona and see what is the temperature. That's where GR is important, right? And that's what we do. So you have, if it is a steep energy spectrum, soft matters. So you have to know E0 very well. If it is a flat, it's ECAT that matters, all right? Okay, in your luminosity, because what matters is what kind of luminosity each the disk point will see. So for steep spectra, it's the soft band, but for flat, it's the ECAT. What ECAT are you going to give into your it's the luminosity that matters. Most of the luminosity is in soft bands and it's steep.
is it sort of possible to have the hard X-rays coming from a different coronal height? So
Right, but that, you mean now about an extended corona?
like yeah,
Yeah. So if you have certification and temperature of the corona, right? We just created now this model and we're testing it. Okay, but then you have far too many free parameters. Already you can do it. Then LSST can do it. You know, if you have now 1,000 making and 1,000 of timelines, maybe there. And it's not just timelines, even variance. Computer variance in physical units can test the model. You can have simple variances trying to black hole mass and dot, and then you have a physical anatomy. And it can even constrain your spin. You can do it as long as you have we did it already for some nearby systems. You can do it. You can test just by variance, computer variance in physical.
Thank you very much.
Okay, I think we better move on to the next talk. Let's thank the speaker. Yes, it is. Yes, it is. So we will now hear from Sean Patano about searching for little red dot candidates that are rich in development. Please go ahead.
Hi, I'm Shun Hatano. I'm a PhD student in Sokendai graduate school. It's a graduate school without undergraduate, so people still know. But I work at National Astronomical Observatory. And I work on little red dots, and especially in Redshift 1 in the DDF. These are my current members on the team. So what's little red dots? It is a JWST found object, mainly Redshift 4 or higher. So this is the picture of little red dots. So it's compact, and it has red color in FP4. And it was named little red dots by Marcin 2024. Actually, they have a Java broad line in the spectra. You see it, and so people think it could be Asians. And by the way, they have a kind of unique spectra in UV and optical. They have B-shaped spectra. It has blue optical and blue UV and red optics. And first, people saw this red component, maybe dust red and quasars, as shown in the red color. And people wanted to check the variability of it. And actually, before that, you can find redshift 0 little dots. It is found last year or 2 years ago by Shinhan. This is the local little dots. So it has the same properties. It has blue UV and red optical, and it has the compact morphology, and it also has a facial profile. And the interesting thing is that they have, you see the weak mid-infrared here. So it has a peak around 1 micron, around 1 micron. So it's kind of different from Rubin AGNs, which have a peak around 10 microns or so. So it has shorter wavelengths. And so it has a black body light which means black body temperatures are around 4,000 kelvins or higher. So which is higher than the dust sublimation temperature. So people are convinced by, kind of convinced by this object that little red dots are kind of different not physical origin. So let's go back to the variability. So people first thought this is AGNs, but they do not show AGN-like variability. For shorter time scale, they don't have variability in less than 1 year, which is predicted to have in the Brandt and Marcin model. And this is a kind of difference image of the results, but they do not find. However, recently, this year or last year, some little red dots are reported to show variability around 10 years or 100 years. And people now think there's a black hole and there are dense gas around it, and it looks like a black hole star or black hole envelope, and people now start to believe that. And interestingly, I'm not familiar with it, but it is predicted to have a Cepheid-like variability. So that's why they may have a variability on long time scale. Okay. I talk about the redshift 1-ish galaxy, little red dots. So little red dots are very common in redshift 4, but actually you can find it also in the redshift 0. But how about redshift 1? So there are research done by UMA, and this is 2025, which is forecast for redshift 2 or larger. But there are not research on redshift 1-ish. And I focus on redshift 1. So actually, you can select little dots from V-shaped spectra. So UV, blue UV, and red optical, and it is selected by different telescopes data. For redshift 0, they use SESS and Galactic, UV and optical, and search variability on ZPF and WISE. While they do redshift 4 larger, they use JWST. But in redshift 1, we can in the future use Euclid, LSST, and Romans, but you can do it now using existing photometric catalog. So what kind of catalog can I use? And I would first use Cosmos 2020 catalog. It is because it has a fairly large area. This is a area of every survey, around 1 square degrees or so. And actually, it has a deep data. So this is a depth image, the depth of the survey. So this black line shows the I didn't read it, sorry, but this is a Euclid PQP1 on depth, while this red shows the Cosmos depth. It's so deep. So you can find the little those in the deeper range. And actually, this Cosmos field is kind of similar to Romans, Euclid, or depth. So LSST depth. So this is why we could start on it. And if you find those, we can search variability using LSST, LSST, because they are observed many times. It's a deep driven field. And also, the good things about this field is that they have a HSC legacy survey, and possibly we can search for a long period of time variability using HSC and LSST. So that's why we focus on this field and around redshift 1. So I will tell you the idea how we can find those. This is the image research done by Iruma. They use RZJK band color. So horizontal axis represents the optical color and reference UV color, and vertical axis represent the reference optical. So they have bluer color at UV and redder color on optical. So little red dots will come into this region. And they found some little red candidates at redshift 0 or larger. This is a completeness of their selection, and they are only found, they can only get a redshift 0 or larger, mainly. So the idea is that you can just shift the color. Yeah. So I change it to YH and GI. So that's it. So this shows you the idea. So if we bring it whether it goes to redshift 1 point, if you wish, you will get these kind of spectra, and the optical color will be boosted to redder side, and it will enter this to this red color region. So I show you the results, preliminary results for it. So the black dots represent cosmos sources, and this is the color selection. Then we see some cosmos objects that shows this color. And I overplot the literate dot's color, simulated literate dot's color, and it surely enters around redshift 4 or so. And the numbers of sources are around 20 in high band magnitudes, varieties in 24 magnitude, while 606 sources in this little bit faint gradient. So I look at it, I just selected, this is a preliminary result, so I just look at the SAD. They have many photometry, so I look at all the 606. And I found some good candidates. So I show you the good one. So this is the SAD for it. This is a reference UV, and this is reference optical. And you see a blue and red. And interestingly, it has a little bit fainter midday for it, shown on 3 micron and 4 micron observed. It looks like black when you see it with your eye, in your mind. It is kind of different from parallel emission, often seen in red quasars. So I brought this because it looks like so. And I brought out image from the Cosmos cutout service, and this is a case band, and actually this is HSDI band, and you see that this source is kind of compact. It is besides the literate dots, people argue that Ilma argues that for example, ULERs or dust obscured galaxies may enter this region. However, you can check the image, and you can ULERs are so big galaxy, so you can kind of exclude those. And I saw it's compact, so I think this is a good candidate. So what's the next step? I would say so I told you there's several each of properties of it, and little books. They have H alpha bromine, but I haven't yet. So we don't have the spectroscopy, so it would be good to follow up H alpha. But for this object, it's always sent to H band and K band, unfortunately. So this object should be followed up by LSST or find next object in different DEFs. We may find brighter objects. And also try to find variety. Yeah. Thank you.
Question.
Hi, thanks for the very interesting. I was wondering, would you be willing to share the coordinates? Because at least for Cosmos, we have, I believe, 14 or 15 year-long life curves now. And they might not be there, but it might be worth giving it a try and see while we wait for LSST if we find some variable sources. Okay, we can talk later if so. Okay.
Questions? Please go.
Very nice talk. I'm sorry if I missed this, but have you considered contamination from dwarf stars, like the white dwarf and dwarf pairs can cause some similar looking SP?
You said white dwarf from the in one. I'm not sure. I'm not familiar with the object, but we have a photo-Z for Cosmos Tableau, and yeah, it uses like 20 or 30. I forgot the number of photometry, so I believe it's a good thing.
Thank you.
Okay, well, one final question, please go ahead.
Thanks for the very nice talk. Is the most of Hermione candidate from like the 600 candidates, or do you have more?
I have a little more. Yeah, but I only checked the HST image for this source, so I just there are several candidates look like the SAD like this, but yeah, I don't know whether it has compact morphology. So, but yeah, 10 or 20-ish.
Okay,
well, let's thank the speaker.
Hello, everyone. I will share my presentation.
So yeah,
Okay.
we'll now have Olena Kompenes coming to us remotely from Ukraine, speaking of isolated AGNs in the nearby universe. Please go ahead.
Hello, everyone. My name is Olena Kompenes. I'm a PhD student in the main astronomical observatory of the National Academy of Science of Ukraine. Here with me also my cat. He helps me and sending to you warm regards from Ukraine. So today I will be speaking about our recent research about isolated active galactic nuclei in the nearby universe and about X-ray properties and the role of environment in a nuclear activity. My presentation consists from two parts. First part, it's about X-ray properties and accretion diagnostics for isolated galaxies in a local universe. And the second part, it's how we trying to estimate local density and also taking into account the cosmic web structure when we're trying to study properties of galaxies. And in this job, we also used SDSS spectra to identify activity class in isolated buried galaxies. So in our department, we all believe that isolated galaxies, it's like universal cosmological laboratories where we can study activity process and ignore all possible influence from entire environment. So the main question is, can nuclear activity be sustained without recent strong external interaction? So what we do here, we used isolated host galaxies from 2MeC catalog and trying to study the nuclear properties using all available X-ray data and also taking into account large-scale environment here. So the first part is here, the X-ray sample. We, in our small sample, unfortunately now, have only 61 isolated AGN host galaxies. So we try to search all available data in X-ray band, which we can use here for study as X-ray properties. And in a result, we use 5 X-ray mission here. It's data from Swift, XMM, Newton, Chandra, STAR, and also Integral, and 20 best fit spectral models. Some of them we adopted from already published result from another scientist because they did amazing job. And some of them was fitted firstly in our paper, in our research. And second part is environment. Environment density of isolated barred galaxies in a local volume. And we also published this paper in Space Science and Technology Journal. And the part about X-ray research recommended for publishing to Monthly Notice and Royal Astronomical Society. So I'm very happy. So you can see on the slide 2 different samples which we are used in our research. So let's start from X-ray sample and data coverage. As I can said previously, we used 20 best fit spectral models and derive the main properties of isolated X-ray, isolated AGN in X-ray band from the spectral fit. I mean about the photon indexed column density, if it's available, because some of the galaxies in our sample is a safer one with very small column density, but some of the galaxies is also Compton thick AGN with very high value of the column density. Here you can see an example of the spectral fit, which we are used here. We use this strategy in this case is do not doing homogeneous spectral analysis, because for our 20 galaxies, the spectra in the X-ray band are very different. Some of them, it's only, as you can see here, like power low plus soft excess and hot gas. Some of them have different X-ray components except primary emission. It's a transmitted emission, scattered emission, and reflection component. So we are, for each galaxy, choose the best model for describe the physical features which we observe in this X-ray band. So the final models include combination of thermal, absorbed, power low, reflection. Some of them have the ferrum iron alpha emission line, and also partial covering and torus component. What was like a surprise at me, because I remember when I started my PhD way, I told to my supervisor that I have my scientific dream that I want to sometime in the future found some object where we can observe the relativistic iron line for working a little bit with general relativity, because I'm very love general relativity. And one of the AGN from this isolated AGN sample demonstrates a quite interesting case. So here for the Swift XRT continuum, you can see that we haven't any reflected component here because we observe in general only power law emission. But after 10 years of this Swift XRT observation, the Chandra observes the same object. And the Chandra spectrum, yes, it's not very nice spectrum. In this case, you can see how big errors here, but that's all what we have in this case. And here you can see that we have some correlative after 5 kV here. So we started to thinking about what it could be possible. And yes, here could be different physical explanation, but for test them, we need better data for mid X-ray, and also we need data for the hard X-ray for having the possibilities to study reflected component and detected, for example, Compton hump. So we need the data from NuStar, and unfortunately they are not available for this case. So we try to estimate some limitation for a model which we can obtain from observation here, and after use this limitation in a Schwarzschild matrix for estimate the different possible physical explanation with the discline model here. And in our paper, we also show that the statistics where when we use the discline model is better. So we can assume that maybe in this object we observe the iron Ka-alpha emission, but unfortunately data is not very nice. So on this stage we can only assume this. For us it also was like a surprise, because when we started working with isolated AGN, we expect that it should be quite weak, because this object weak in an optical band. So we assume that we will have the similar situation, weak emission in X-ray band, and we definitely do not expect some quite interesting physical case. We also used available data from spectral analysis for estimate the mass of the black hole here, because we need this parameter for continue working with the accretion diagnostics. So we combine in our paper and also in this research our own estimation of the supermassive black hole mass, and also we used available estimation from the literature where they try to estimate the supermassive black hole's mass with another methods. And what we can show here, unfortunately, also it's not available data for all objects, and we hope that the future LSST data can help for us improve this very bad statistic, because for most isolated AGN now we had very low quality data. That's why we are used in X-ray band, and also in another, for example, optical band, we haven't quite very nice statistics in our results. And you can see here main X-ray trends. So we adopt the relation from Young et al. For X-ray band, where you can see two different accretion regime. The green value is accretion regime, which according to the EDAF and type 1 LHAF, so it's in a one-phase accretion model, one-phase accretion flow, I apologize. And the red here is two-phase accretion flow. And what was also surprised for us that these isolated galaxies, they haven't some one type of accretion. So we are observe here that our isolated galaxies, which we are studying this work, they have a broad regions and broad values of different accretion flows and also Eddington accretion rates here. And also the luminosity in the X-ray band, it's like a typical for luminosity of Seyfert galaxies. So based on this result, we can assume that we do not observe the evidence that the environment have some influence to the activity of the AGN in our isolated galaxies. We also know that we should test this with more bigger sample, but now we have data only for this small part. And after the discussion with reviewer, he or she also recommended to us to study in more details column density. So you can see here we overplotted the value of column density for isolated AGN on the original image with the different sample of early merger AGN and late merger AGN and also Swift butt AGN from the Ricci et al. So the second one, yes.
We're running short on time. If you could wrap up, please. Thank you.
Okay, I will be very quickly. So about our result with environment influence, we used the different method for calculate the environment properties, and the estimate density is the best way here is 3D Voronoi tessellation, but when we haven't enough data for using 3D Voronoi tessellation, we used 2D Voronoi tessellation or k-nearest neighbor. And here you can see how the most isolated Barrett galaxies occupy voids or filament and the distribution for this part. So the most galaxies are located in a voids, but small sample here we can see that located in group and the cluster. So we should now reclassify more past isolated AGN catalogs here with all available data. Here you can see how it looks like our approach with the Voronoi tessellation. So we can reconstruct cosmic web environment and taking into account when we estimate the large-scale properties of the galaxies. And we also use the available spectra from the SDSS for classify this sample of isolated galaxies, and we can see here that for this sample we have different part of activity types. It's a liner, Seyfert's, composite, and also star-forming galaxies, and we plot our results with different activity types together with the properties of the density, and used Kruskal-Waltz-Ash test and didn't find any statistical difference between this activity class here. So we can conclude here that the local density does not significantly differentiate the liner and Seyfert nuclear from star-forming or composite system. And here you can see the main conclude, and the main hope for me is that we can use the LSST data in the future to refine 3D environment metrics and put more cosmic web context in our research, which are related to the influence of the local and cosmic web environments to the galaxy evolution. Thank you. May the science be with you. And if you have any question, please contact me.
Thank you very much. If I understood correctly, it's all spectroscopic redshifts, but did you do any tests with environment reconstruction with photometric redshifts?
Can you repeat last, because the connection is not very nice?
So the environment is based on spectroscopic redshifts, correct?
Yes, yes.
Okay, did you do any tests with photometric redshifts? Can you construct the environment?
We're thinking about this because I'm also working with Seagull, so we can use all available photometric redshift, and also we can estimate another properties from the multiviolet analysis for isolated galaxies, but it's a new part for me. And the main problem here is that I know that we can use the photometric redshift also only in a local universe, because the difference between the photometric and spectroscopic redshift for the more early universe is quite big.
Okay, thank you very much.
Let's thank the speaker. Okay, we will now hear from Colin Burke, who will tell us about AGN variability as a new cosmological probe.
Okay, thank you, Neil. So thanks everyone for having me. So this is work that I did with Iossif, who's a graduate student at Yale, Priya Natarajan, and Wei-Chang Yu. So trying to turn AGN variability into a cosmological probe to try to get beyond what we can do with other low redshift probes like Type 1a supernova. So I had to learn a lot of cosmology to do this project, so that was fun. So I thought I would just kind of start with a little bit of motivation. So this is the kind of the modern day distance ladder. So this is view, or the luminosity distance, distance modulus on the y-axis, basically distance of the supernova versus redshift. So how to calculate, how to make this Hubble diagram. So you use this equation here, which relates the distance modulus to the observed brightness, the paramagnitude, and some way of predicting the absolute brightness or absolute magnitude in a cosmology independent way. And so for Type 1a supernova, they are not perfect standard candles, so a lot of corrections are needed to the data using this famous trip equation, like the color and the stretch of the light curves, and correct for dust and things like that. There's also Malmquist bias correction, and even a dependence on the host galaxy stellar mass. So anyway, so the idea is, can we come up with an analogous relation for variable AGN? So this is so basically you want to calculate this residual. You compare your calculated distance modulus to some model, and then you need to calibrate it because you don't know this fiducial offset to something else. So further down the distance ladder, right? And so usually that's done using Cepheid variable stars, and basically you minimize the square of this residual normalized by some covariance matrix, and you jointly infer that with cosmology. And all of the modern papers use Bayesian methods to do this, and you just plug in your luminosity distance equation there and infer your cosmology using different models. And so this, the famous accelerating and expansion of the universe, is a deviation from this straight line on this Hubble diagram, and that was found really by with HST famously, and going at redshift greater than 0.1, where you have more leverage in these models. This is a more recent paper from the Dark Energy Survey using a somewhat more homogeneous sample. And so, again, this is the Hubble diagram and the residual on the bottom compared to different cosmological models. And they're sort of standard models like flat, lambda CDM, and so on. And the cool thing is, some of these recent works, including most famously from the baryon acoustic oscillations from the DESI experiment, are starting to find hints of needing to put in some evolving dark energy prescription into the cosmology at a 3 to 4 sigma level. And so you can see from these models that the precision you need is, much tenths of a magnitude, but it does get a little bit more leverage at higher redshift. So that's the goal. And Julia did a good job of explaining that a couple days ago as well. So this is the CPL model. This probably the simplest model that you can write down, letting the dark energy equation of state vary with redshift. Just this kind of linear variation with a scale factor, or with redshift, using this equation. And really, you can only start to see the deviations at higher redshift. So redshift greater than 1 is needed. That was recognized even in 2001 in this paper. To really distinguish between these two different models. And so we want to use AGN because they are more luminous and can be found at higher redshifts than SN1A. I think even with a new generation of telescopes, you will not find many type 1A supernova beyond slightly more than redshift 1. AGNs are much more difficult to identify, but fortunately they are worse standard candles because they have a range of luminosities. So also we might want to use AGN because I think their SEDs and properties are kind of surprisingly universal with redshift. Once the selection biases are taken into account and you correct for luminosity and Eddington ratio correlations with redshift. So if you fix the luminosity, Eddington ratio, things like that, those other parameters, do see some correlation with redshift. So this might be the most sketchiest or kind of most controversial thing, but if we can find, they do evolve with redshift, but when you control for the other parameters, is there an evolution in redshift? So that's kind of the question. So we want to control systematic effects with redshift first. Also want to point out the previous work done by Risalite and Lusso and collaborators a few years ago using the alpha OX relation. So this is the relation between the UV and X-ray luminosity fraction and the UV luminosity. And so this paper inspired a lot of this effort. However, there's kind of a large scatter in this correlation, partly due to the self-correlation with UV luminosity and luminosity, but you can beat down that correlation by large numbers. So we have large numbers of AGN, for example, in stripe 82 that we're kind of working with here. So this is the analogy with Cepheid variables, the stars. So this is on the right, it's the Cepheid, the Levet law, do not call it. And on the left is AGN, damping time scale, and luminosity correlation from Kelly 2014. And there's also the correlation between the amplitude of the variability of the optical light curves and the luminosity, again, from the same paper. So we actually combine these two correlations and make a 2D or 3D correlation using the amplitude and time scale luminosity. So that's one of the ways we're able to get a little bit of a better correlation rather than treating them one by one. This is also was pointed out to me recently that even in the 1970s, there was a correlation between the RMS of the light curves and the luminosity from Angioni Smith, 1972. So not a new thing. So here's what this actually looks like. So you all know, so this is the AGN variability looks stochastic, but we can still infer their properties, for example, by fitting Gaussian processes or looking at the structure function or PSD. And this is the Cepheid light curves. This is phase, but you get the idea. So can we build an analogy between them? So Weizhang was kind enough to provide his light curves. And the important thing is that he has collected the multi-band light curves. So we can look at how the light curve variability changes with time and also with wavelength between the different bands. And we use kind of a DRW-like kernel that can steepen a little bit on shorter time scales. But we want to eliminate this K correction, which can mess up your redshift thing on the Hubble that can look like a redshift evolution, right? So it's important to get the multi-band covariance correct. So the model that we use is a Gaussian process where you have covariance between bands or the rest-frame wavelength and time, and then additional components. So we use basically DRW like time covariance, and then we assume that those DRW parameters can vary with rest frame wavelength according to these kind of power law, simple power law correlations or scaling relations. And then we assume there can be some additional component from something else, probably the broadline region. And so that actually matters because if you don't correct for this, you get wiggles on the Hubble diagram from the color variation of the variability due to the VLR. So you kind of had to do photometric reverberation mapping to do this. So I don't have too much time, but this is the rest frame wavelength correlation of our sample. And I think there are different ways you might interpret this, but we see the famous anti-correlation between the variability amplitude in a given band and luminosity, or in this case, the rest frame wavelength of the disk. And so one way I like to interpret this is I like the model of kind of toy model from Dexter and Agel, 2018, where you have a Keplerian disk with local thermal fluctuations from intrinsic variability in the disk, and it's rotating in Keplerian fashion. That will lead to inhomogeneities in the disk. We have different inhomogeneous emitting zones, and those zones can be maybe varying independently. And then depending on what radius you're looking at, you're going to be averaging over more of these independently varying zones. And so that will reduce, just like the average over a large statistical sample, reduce the amplitude of variability or the scatter in your variability at larger radii and for more luminous disks. So this is the full 2D correlation across the sample. In Stripe 82, we have around 6,000 objects. This is the 2,500 angstrom luminosity measured from the spec. This is just, we don't actually use this luminosity in the Hubble diagram. This is sort of a consistency check, assuming a cosmology. But this luminosity is measured from the spectrum, apparent magnitude at 2,500 angstrom, then assuming a cosmology, just for purposes of making this plot. And the correlation there between the variability amplitude and the time scale, again, at the rest frame 2,500 angstrom. Thank you. And so this all correlates with, or might scale with the size and the luminosity and the mass of the disk in kind of a complicated way. And you can use some Venn disk theory, which may not be that accurate to kind of try to interpret this. But the point is that if the time scale and the amplitude of variability properties scales with the size or the geometry of the disk, then you can have something like a standardizable candle. So we have 6,000 AGN in Stripe 82. We looked at the spectrum for all of them. This is also pretty important. So, I thought this would not be too hard, and then I started looking at these spectra, and I was like, man, this is such a mess. You have you want to see the accretion disk continuum, right? Because that tells you that the variability that you see is coming from the disk mostly. But a lot of things have, the host galaxy emission is dominated by the host. So that's mostly affects your lower redshift objects. So we tried to remove those and did a lot of tests to make sure that's not affecting us too much. Some objects have crazy broadened iron emission everywhere, and we will get rid of those. And the vowels at higher redshift, so it's pretty nasty. But we tried to come up with a clean sample at the bottom example where you have just power law continuum, where we think we're seeing into the accretion disk. So this is what we mean by type 1 AGN. By the way, I'd like to advertise a new code we wrote. So this is a version of PyQSO fit that we use for the fitting. That is fully Bayesian and does the host decomposition at the same time as the AGN. So this helped us a lot to do this modeling in a much more robust way. So if you're interested, this is public on my GitHub, and welcome collaboration and contribution to this code. Very fast and gives you nice Bayesian posteriors for everything. I'll skip the selection bias thing because Julia explained that very well. So this is our Hubble diagram, and we tried our best to minimize the chi-squared at the bottom, and that's where we got. And then you can make, this is the VLR subtraction. You can ask me about that later. And so the cosmological parameters that we obtained from our model, we find a very high omega matter that's kind of difficult for me to interpret. And we find a strongly negative WA, which tends to drive your fitting toward maybe this kind of degenerate solution, but other samples find fairly consistent results, which is actually kind of reassuring. And we have a table of all that I can show you as well. And so by comparing the Bayesian evidence between these different models, back here, which are shown at the bottom. So this is the relative residual to our best fitting model in magenta, which is the evolving WOA model, evolving dark energy. And so that tends to fit the data better than if you look at the relative residuals of the dashed and dotted lines. Those are W, CDM, and flat CDM. So we tend to find sort of 3 to 4 sigma evidence for the evolving dark energy, which is very exciting. So, okay, so in conclusion, I think we should start to think about what we can do beyond type 1a supernova, and hopefully AGN are an exciting prospect because they're very luminous at high redshift. And we're only at the beginning, so I welcome future collaboration to test these systematics and improve the techniques. And the more we learn about AGN variability, the better it will get. So, thank you.
Have time for question. Go ahead, yes. Yes, to that, yes.
Hi, thank you so much for the talk. Have you tried for the cosmology, like when do you get a view sample on the W5 pivot? Like instead of W,
pivot redshift?
Yeah.
Yeah, so I think I tried that and it didn't affect the results.
Okay.
So yeah, I know this is saw a little bit of arguments in the literature about whether you should use this pivot redshift or not, and that helps you constrain the degeneracies. But I don't think we saw a big change when we did that.
Okay.
Thanks.
Other questions? Could I ask? Oh, please go ahead. Please go ahead.
I was just wondering if your result, depending on the model that you assume for variability, is based on Ampron of walk, or this can be generalized.
Yes. Great question. I think the next step would maybe be to try Wei Zhang's SHO model and see if that changes things. We did do something a little more complicated than a DRW, so it is kind of more like an overdamped SHO, so it can steepen a bit, but it can't give you this extra bump that Wei Zhang found at lower velocity. So I'd be surprised if it changes things too much, because we really only care about locking onto that break in the PSD, but it would definitely be worth trying. It gets hard to do the full SHO, because you also need to think about, if you add many parameters in your kernel, you need to think about how those might change with wavelength as well. So that can be trickier to write down.
Yeah. Okay, great. Well, let's thank the speaker.
Right, thank you.
Okay, for the final talk of this session, we will have Julia Erseg, who will tell us about modeling close galaxies of variable AGN triplets. Please go ahead.
Okay, thank you. Good morning. Firstly, I want to apologize for my voice, firstly, because I'm Australian, and second of all, because I'm recovering from a cold, so I could have practiced this morning. So, yeah, my name is Julia Erseg. I'm a first-year PhD student at the University of Southampton, and today I want to show you some work I've done modeling host galaxies from variability-selected AGN using the DP1 compound images. So I want to initially motivate why we need to be looking at host galaxy contamination, especially at low redshifts in the LSST era. I'm going to talk through the candidates that I'm using, what their colors look like, what their images look like in the DP1 catalogs, and what host decomposition we're able to do at this stage. So just taking a quick peek at the images first up, it's really clear that we can't be treating these LSST AGN as point sources, right? I mean, sure, these are at low redshift, but still we can't be just modeling them like QSO objects. So for this work, I initially took a variability selected sample from LaCierQuest in the ECDFS field, so I've got about 1,000 candidates to work with. I then cross-matched this to the Zootel catalogs to get some photometric and a couple of spectroscopic redshifts. Additionally, I then also took some HSC and voice and video magnitudes for comparison from the Zootel photometry catalogs. Once we then cross-match this to DP1, because it's such a small field of view with the ComCam, only get about 62 objects, unfortunately, and with quality cuts for anything that's on the edge of images, we only end up with about 53 objects. This is sort of the distribution of them. So as you can see by the RA and depth, it's a really small field of view with the commissioning camera. But you can see essentially how the CCDs are set up. And so you can see some of these deep coad stacked images on the edge of the patches aren't necessarily completely covered. So that's why I've had to cut some sources out on the edge of the field of view. And again, because these are just AGN candidates, it sort of cuts down the sample size even further because we've only really got, a handful that are actually definitely reliable AGN based on their SED fitting and having X-ray and infrared counterparts. Potentially a good chunk of these might be quiescent galaxies, and there's a couple of stars as well that have popped up. So all of the decomposition and the color analysis work that I'll show you are just based on a reliable SED AGN sample. So if we just plot straight up the PSF magnitudes from the DP1 catalog, this is what we're seeing. Everything in black is the spectroscopic redshift associated. The gray dots are the just the photometric redshifts that we have for the sources. This is plotted against Matthew Temple's QSO Gen code, where I've got some QSO model tracks for different dust extinctions and galaxy fractions there. And you can see, especially at the lower end redshift, they are not matching what we're expecting to see at all. Obviously, it's still not fantastic at the higher redshifts because of the image quality, but it's in better agreement with what we see at the low redshifts. And this is just further motivation that we need to consider the host galaxy contamination at these low redshifts. So if we just want to take a quick look at the images, because I know that we will do the theory and the simulations, but we do actually have images to look at. This is an example of what one cut out from a patch looks like. It's very pretty. Unfortunately, I just look at this little dot, for example, but I'm going to use this as my case study here. It's quite point source-like, but it is a reliable SED AGN. So this is what we're actually seeing so far with the commissioning camera. It's really important for me to be able to select what band to work in based on the scene. The better scene we have, the better resolution of post decomposition I'm going to be able to do. We are only getting below 1 arcsecond seeing in the I band at the moment. Really, I want something more like 0.7. But I do know with the on-sky LSST-like test that they're doing at the moment, I think they're getting about 0.45 for width half max BSF, which is pretty good. So that's why I selected to work in the I band. And then with the depth, we are actually getting down to 27 already in the commissioning data, which I feel like not many people know about. That's really impressive considering this was like 30 days, right, of on-sky time. And that's mostly in the G band, but again, because I need to prioritize that resolution, I've decided to work in the I band, which also has pretty good depth. And you can see how in the stacked color images, we obviously have improved depth towards the center of the field of view of the camera. All right, so I'm just going to quickly just give a brief overview of this because obviously Shenli Tang explained this quite well and in depth yesterday with his work. But I've been using Galactic, which is an open source Python package that does sort of 2D model fitting just for light decomposition. It's perfect for optical and near infrared, which is great for LSST. And this is an example from Shenli's paper from 2023 where he was looking at binary AGN systems and has done some decomposition work with HSC images. So this is the method that I'm going to be using to decompose the host. So this is that example, that very point source-like AGN that I showed before. On the left, you can see the data that was inputted, the model it produces, and then the data minus the point source, which is the remaining host contribution. Just noting that this decomposition was done in the I band. As you can see, it has quite crudely masked some nearby objects, so that's what those black spots are. But this is an X-ray and it has a mid-infrared component confirmed. It's at about 0.6 redshift. And so if we look further at the model, this is where some of the issues come in with just the image quality. In the DP1 catalogs, it's a contribution of both, poor image quality, but also the data reduction isn't fantastic. I tried with a collaborator, Elham, to run some HSC images through the PSF pipelines, and it doesn't seem to be pipelined so far with LSST. That's the problem. It's actually just the data reduction from the image quality. And so you kind of get this weird pattern that comes around the model that Galactic picks up from the host. So if you're just looking at magnitude, it's not a problem, but if you want to look at morphologies, which I was kind of hoping to do, it's not really at a stage that you can do that. If we look at its color, it sits about here with just the DP1 magnitudes, just the PSF flux. If we then look at its I-Z color, once we've done the galaxy subtraction, this sits a lot closer to what we're expecting just a pure PSF to be. Obviously, the host galaxy fraction, the contribution does sort of change depending on what band you're looking at. So this shows exactly what I was expecting. The colors get bluer as you do the host galaxy subtraction and fits better with our original ideas of what the AGN model colors should look like. This gets messy though. When you work with poor quality data, as you can see, the high redshifts, it just does whatever it does at the moment. For some reason, obviously just the I band, for example, for one of them at the higher redshifts, obviously the image quality was much better, so it thinks it's redder without the host. Go figure. But at the lower end, we can see that in general, when you subtract the host away, the color is getting bluer, which is what we expect, and it helps push the color of these sources in agreement a bit more with our previous QSO models. Obviously, this doesn't always necessarily work at higher redshifts. So with this work, even though we know DP1 isn't necessarily supposed to be science ready, we can still do some modeling and get an idea of what the objects are looking like, how much host galaxy contamination can we expect, and how we need to adjust our models to take that into account. The current limitations are absolutely with the image quality in PSF, but as we get better seeing, which we definitely will with the full camera, definitely will have better host decomposition to make this a lot easier. And yeah, it shows evidence of host galaxy contamination in the LSST era, and I'm hoping once we have better quality data and I can actually look at some more of the morphologies, I'd also really like to look at the influence of the AGN's variability as well, using LSQ data as well. Thank you.
Thank you. I have a question related. How's the background is subtracted in your modeling?
So basically in Gala, everything works essentially as a free parameter.
So you hit the background as well?
What you can do is you can set free parameters of like, okay, I need a pixel to be at this level of flux, and I need this many pixels to in the neighborhood size to select it as an object, and then it subtracts everything that doesn't fit that criteria as background.
Okay.
Does that make sense?
Yeah, I just wanted to know basically, are you fix the background? I mean, do you fix the background, or do you actually treat the background as also the sort of the free parameter? But it looks like you're handling the background, depending on the sources, right?
Yes. So it essentially selects the source first based on the parameters that you set, or that it sets, and then it subtracts it.
Yeah, and your PSF is, how do you construct your PSF?
Through just from the LSST pipelines. So for example, it'll literally look like this. Is what I would input is I would take a cutout, it fits a point source and a CIRSIC model, and then I'm just taking the PSF model for that particular, it would be the central pixel. So with the LSST pipelines, every pixel has its own PSF.
Okay, so
that the pipeline generates. So I'm taking then, it would be the central area of the object. I'd select that pixel and generate a PSF model from that. And then input that into Nuclei.
Yeah, it makes sense. So that's why you need a better quality images.
Yes, yeah. I also tried creating some manual PSF models from Gaia, but again, the docker function is a little bit tricky.
Yes, please go ahead.
I'm just curious, is the resolution of LSST image sufficient to perform such image decomposition?
To do the host
without optics, yes.
Yes, yeah.
The resolution is sufficient?
Not at the moment. That's sort of, yeah, the point of what I was showing is that we can do some decomposition, but it doesn't work for all sources, especially at higher redshifts, where we just can't see it as well with the commissioning camera.
Because we face problem even using active optics, so that's why
Yeah.
I'm just curious.
Yeah.
Yes, go ahead.
Thanks. So this was all deep co-added images, I
Yeah.
presume. So did you look at the single visit images and you could
in-
select the best BSR from or best seeing single visit images?
That's what I want to initially, eventually do is I want to create like best seeing stacks essentially, because for the deep coeds I take like just essentially the best depth of single visit images and stack them. So it would actually be really handy if I could create best seeing stacks. I know there's the lensing science collaboration here. I was talking to someone about that. They're also interested in that. So that's something I'm hoping to do in the future. I was more so just going to wait to see what the seeing looks like in DR1 and then go from there to see if that's necessary to do. But that is an idea I've had. Yeah.
Okay, then a quick comment that all of the field is covered in the Univ Q1, so you have to be seeing images as well, so you
Yeah.
can use that as a control.
Yes. Yeah.
Okay, thank you. Oh, please go ahead.
Very fast. I just want to encourage people in cases to try to see if there are LSST data for this field. They may not be better and so on, but they're there. So if you want to check something of the images or something, go there, download a couple of images, we have the stats and so on.
I had done that for HSC.
That's all for you. Okay.
Yes, yeah, I had done that for HSC and I went through the sources just to see if they also look extended at HSC.
Okay, great. Well, let's thank the speaker and we now have a copy.
If we start now, I was before That's not the point. Are you straight? Yeah.
Thank you very much. I don't want to see it. So move that. I don't.
Yes. Okay, so we can get started before that they have a very brief announcement. Because we missed some people for the conference picture yesterday. So sorry, you guys, we couldn't have waited another 5 minutes. We will take a second and we will mix them with AI. So we will just get, before lunch, we just gather downstairs at the yard, and someone will take it from the balcony. And that's the announcement. Meg is the first speaker of this session. Please take it away.
So hi, you've seen my face all week, and now you finally get to hear what I do for research. Congratulations. Hi, I'm Meg Davis. I completed my PhD last year at the University of Connecticut, where I worked with Jonathan Trump, no relation. I actually left academia for 8 months to work as a machine learning engineer and data scientist in private industry, and now I'm on my triumphant return to academia, working as a postdoc with Maria here at IA. Today I'm going to chat with you about my work on binary detection in the Rubin era. So this is going to be a really brief overview and also an advertisement. You'll see. I'm going to start my talk the same way I'm going to end it, and that is with a thank you. Thank you all for being here, for registering, for participating in the discussions, engaging in each other's work, and being present as we collaboratively work towards AGN science. I'm quite excited for what's coming next, and we get to do this all together, and it's quite fantastic. So thank you. Now, for the science. Brief, because you've heard enough binary talks already this week, and you're going to hear at least 2 more after this, so let's go quickly. Binary supermassive black holes form from galaxy mergers. Here on the left, I have examples, real examples, images from SPSS of dual AGN, varying degrees of nuclear separation, kiloparsec to parsec scales. Through dynamic interactions with stars, gas dust, other compact objects, these black holes, those nuclei work themselves down to parsec to subparsec scales, eventually become gravitationally bound as binary springs and start emitting gravitational waves in the gravitational regime. Finding them has broad implications for many areas of physics. A couple are there. The issue is photometrically, optically. Again, photometrically, optically, that's my work. All the other regimes, spectroscopic, not me yet. Okay. We have hundreds of candidates, but no full confirmation of detection yet. And over the next couple slides, I'm going to show you exactly why. So first, as you all hopefully know, active single supermassive black holes are intrinsically variable. Damp random walk, all models are wrong, some are useful. Yes, I'm using the damp random walk. Yes, we can use other models. That's my work. Okay. And I move forward because we've heard a lot about this already this week. And also, as we heard, binary supermassive black holes can produce periodic signals in many ways. A favorite of mine is the Doppler boost. The Doppler boost can produce a smooth sinusoidal wave that can modulate the light curve and indicate a binary. Okay. Now, just a few slides ago, I thanked you for actively engaging in people's research. You're going to do it for mine. It's now audience participation time. Before you, you have 2 synthetic light curves. We're looking for periodic behavior in noise. I will not tell you if there's a binary on the screen. Both could be single AGN. Both could be binaries, or one or the other. In about 10 seconds, I'm going to ask you all which one you think is a binary or not. So, okay.
One must be.
They
Maybe.
both could be neither.
They could be both, could be neither, could be one, could be the other. Okay. Time's up. I think it's the one on the left. How about the right? Both? Neither? Okay. Folks online, you're also welcome to participate in the chat. You have about 2 seconds before I read the answer. No luck. Very few people. And because for the AGN Science Collaboration, we like to have fun, here's going to be the Penn. And I'm going to give you more information. Below each of these plots, new light curves, more information. I've applied detection methods and given you the results of those detection methods, whether those detection methods have determined whether or not the light curve is periodic or non-periodic. I'm going to give you less time because now you have more information, figure out how that works. Who thinks it's the one on the left? The one on the right is the binary. Okay, that's the question. Okay. Both? Neither. Okay. Sometimes our methods work. Sometimes we don't. As you can see. Sometimes we do. So thank you all for participating. You're all off the hook. You no longer have to give my talk for me. Thank you so much. We can't confirm detections of binary supermassive black holes because quasar variability is producing a false positive detection for us. So a lot of our methods fail because of that quasar variability. Yeah, kind of your quasi-periodic as well. Thank you. Optical photometric detections are also going to need multi-wavelength and multi-messenger confirmation, in my opinion, for full confirmation of all those candidates. And all of those wavebands and all those multi-messenger detections also have their own positive contamination and other ways to take a binary when they're defined. Nonetheless, I still have hope that we're going to hopefully confirm the binary supermassive black hole. Hopefully in my lifetime. That'd be cool. Nonetheless, finding them will fund my research. Hope comes in many forms, but my favorite, of course, is Rubin. We could expect hundreds, thousands, maybe 10,000 or so binary supermassive black candidates. It depends on who you talk to and the projected rate of binary supermassive black hole expectations. Rubin, however, is going to produce 10 plus, up to 20 terabytes of data every night. And while we're not going to see all of that data in one go, of course, we do need fast detection methods. We are truly looking for a needle in Rubin's haystack, right? 20 million AGN. Beautiful light curves, long duration, high cadence, especially with deep drilling fields. It's going to be ideal for finding binary candidates, especially when coupled with ZTF and previous observations from other telescopes. But we still have issues and we need fast detection methods. So the bulk of my work for answering these questions: how can we prepare for Rubin? How can we triage those single quasars that all of us got tripped up on just a few minutes ago? Are there any types of quasars that give us trouble? And what can we actually reliably detect when we inject those binary signals into light curves? One of the first things we have to do is, of course, Rubin's not online yet. Sad, devastating. We need data. So bulk of my PhD work was simulating millions. And on my laptop right now, I have about 25 million light curves for Rubin. With broad ranges of quasar and binary properties, you pick a variability model, you pick a periodicity model, combine them, and then simulate the LSST PDF or like I see a light curve by applying those observation tasks. Through my work, I also updated these to reflect the AGN number density expectations for Rubin and also quasar luminosity functions, those got injected as well. It's follow-up work. But we needed data. And we have more beautiful light curves coming from Eden. He chatted with us like 2 days ago, I believe. Beautiful multi-band light curves. They're well on the way, and we all get to use them very soon. So we get very excited about that. So once we have data, then we get to start throwing detection methods at all of those millions of light curves. This is an example of very simple sinusoidal curve fits. I'm talking 3 lines in Python, LM fits. Applying sinusoidal curve fits to data, we shouldn't just be applying sinusoidal curve fits to, because astrophysicists like to do that. On the top, we have a single isolated quasar. If you close one eye and squint a little bit, yeah, there could be a long period in that light curve. And if on the bottom, we have a true binary light curve. Kind of detection methods like these. And again, my work is focusing on fast detection methods. I can fit 50,000 light curves a minute with this method. If there's a binary, we can roughly recover the binary parameters with even a simple sinusoidal curve fit. However, you have to mess with the definition of what a false positive rate is, and then there's a lot of contamination. So it's a flawed method, but it does work, and we could use it for triage. There are other methods that we could throw, of course, but before that, we actually investigate the quasar and binary properties and determine where our methods succeed and where they fail. We have other methods, like I said, exploring questions like what happens if we treat the binary detection problem as a binary classification problem. Throwing traditional machine learning, so full random forests, all the way through deep learning models and 2D CMNs, and seeing what succeeds, what fails, and what do we need to do to make it succeed better and work well with other detections. Here is an example of a confusion matrix of some work that I'm currently working on. We have what I'd like to draw your attention to, a 1% false positive rate and a roughly 70% recovery rate, true positive rate for binary detection. This is doing all right compared to most of our methods. Hilariously, using a random forest, which is what that confusion matrix is from, 45 minutes of training, decent results. Using a bigger, beefier, deeper learning model like a 2D CNN here on the right, 85 hours of training, worse results. So maybe we don't have to overcomplicate things too hard. Maybe we can just use a random forest. We move from single band to multi-band, expanding all the Rubin filters may give us advantage in binary search. We can use other methods like periodograms. Here I have an example, multi-band light curves, single band periodograms with the multi-band periodogram. We continue to get those detection rates, but also now get to explore too. Performance is a function of survey design. What happens when you change the cadence? What happens when you change the baseline? And what's next? I promise I'm almost done. Hi, I'm one of your fearless leaders of the Periodicity Search Task Force. We work very closely with the Binary Follow-up Task Force, and we're actually about to begin a code comparison project. Okay? We'd like your help. If you have a periodicity search code, we want you to come join us. Okay? Here's the Slack. Here are the other leads, Maria, even. We're quite excited to build these reliability profiles and start stacking methods because some will succeed where others fail, and we get to work collaboratively on this. So in summary, thanks. Come join us.
Questions?
Maybe for the result. I was wondering, like, how long do you need your light curve to be to actually make sure that you have like a period there and not just like stochastic in the AGN? Yeah, good question. Typically, sorry for flashing this up without explaining too much, just for time. We like to have at least 1.5 signals covered. So it depends on the binary signal. We want the statistics on whether or not this is a true period and a persistent period. So we need at least 1.5 cycles to be good. Statistically. More cycles of the period, the better. Yeah, of course.
Hey, thank you for the great talk. When you do this test of different codes to draw periodicity from these light curves, how are you going to treat computations? Because I feel like they need it very, very, very vastly.
Yeah.
And also in the true positive rate, but those tend to be a little bit closer. So how are you going to compare that computation efficiency?
Yeah, it's a really good question because we're going to work on figuring that out together as a task force. Some of these methods are quite quick, but they're not statistically robust. So are those our triage methods? Where do they go in the pipeline? And also, okay, do we triage and then get to feed as follow-up all of those light curves, those triage to the more computationally expensive methods? I think that's what we're going to end up doing in the end. But it's going to be really tricky. And honestly, I'd love for more of you to join us to chat about this. And we just had a very lengthy discussion on the way. How about computation yesterday? This is going to be a problem we're going to be facing, and I can't wait to relay a lot of those statistics, especially through the code comparison project, about our computation needs as a task force to do this problem.
Thanks, Meg. Can I pick up on the survey cadence feedback and ask how rapidly you're able to provide feedback on survey cadences? The context for this is that I think some people have seen this already. I don't think it's been explicitly mentioned out loud in this room, but the version 5.3 survey simulations were released about 36 hours ago. And there are a couple of variations within there that it'd be good if we can get sort of rapid feedback on what would be good for AGN science, if anyone's interested in that. There's also a survey cadence workshop planned for June to sort of look at those cadence simulations. So if you're willing and able to get some results on that in time, that'd be really good.
For binary detection, our biggest thing typically is baseline. The longer the baseline, the better. And it really is detection method dependent. This is an example of what happens when you engage cadences with the multi-band kilograms and single cadence helps, of course, in a more rapid cadence, but it's actually the biggest effect is actually this. But by doing this work and testing everyone's periodicity search methods and making sure that we test out surveys, and we can probably get some feedback.
Okay, let's thank Meg again. We've also going to talk about periodicity.
Oh, it's
No,
I don't need the. Okay. Okay. Hi, everyone. I'm Yu. I'm a postdoc at Bishop University in Canada. So today I want to talk about or introduce you to our work of doing scalable systematic searches for quasars have quasi or periodic variability or movement with easy size. Okay. So I want to thank SMAC for giving such a wonderful talk. So it makes my life so much easier to explain the challenges we're facing to do systematic SNDHB searches using like this. So, next one. Also, to all the previous talks of talking about supremacy black hole binaries, I don't have to give a introduction to the motivations behind that, right? It's very exciting to look for those for multiple reasons: gravitational wave detection, multi-messenger astronomy, dream gauge physics, standard Saturn cosmology. The very bright future science can do with those things. Okay. And Charisi has predicted that supermassive black hole binary actually creates this, right? So they are expected to show periodic or quasi-periodic variability in their light curves. So due to many different mechanisms, for example, this could be due to the binary is modulating the accretion on the black holes, and so the accretion rate changes, showing some kind of periodic behavior, and that will translate to luminosity. Here shows something from the simulation. The black one is the accretion rate variation, and the blue one is the luminosity variation. In addition, you can have two black holes in a binary, and you're just looking at some inclination, and the brightness from the accretion disk of one of the black holes will two. They will get brighter and closer as moving close and later. Right. Hopefully, we're all convinced that at the moment we should do this kind of searches using Rubin data. And there are so many challenges. I will just give a quick summary first. In the past, people have using Lambsgargo to look for previous different quasar light curves, but it's unknown to be an issue because the now assumption is the Lambsgargo, right, is this Wendels, right? It's comparing periodic with Wendels. So the quasar intrinsic variability will give you a high false positive rate, and you see a lot of false positives. And more recent works from Niel et al. 2016 also shows that actually Lambsgargo fails to select true positives, which is even bigger issue than, in my opinion, the high false positive rates. And there are ways to get around that, which is perhaps doing joint fitting of the retinous part of the variability and the periodic part of the variability. But it tends historically, so it's very slow on the order of hours. From a few very, from some talks that's a given in this workshop, we see this probably has gone down by some factor, but still I would say on the order of tens of minutes or 10 minutes, a few minutes, right? On single band micros, which not scalable or very hard to scale to LSD data sets. And lastly, there's lack of multi-band approaches because AGN has this band-dependent variability, amplitude, and they have interband lags. And Rubin, one thing I have to point out is Rubin only gives you 3 cadence if you combine data from all 6 bands. In individual bands, it's only 20-day cadence. So, yeah, we should take advantage of all bands. And here is where EZTIS come in. So let me play this again. I like this. So EZTIS come out of the Canadian in-kind contribution. The goal of this software is to use Gaussian process to fit a multi-band agent light curve to simultaneously infer the PSD of vector interbands and also measure the interband lengths. Okay. Also, in a very scalable way. So just a quick slide to demonstrate what EZTIS actually does. If this is shown, is a simulated DRW light curves. We put in the wavelength dependence of the amplitude and time scales, also interband length, and here is just a fitting to the actual light curve, which is shown in black, and here is both the input in black and the recovered, the PSDs. Again, we're using DRW very simplistic, but we're showing we can do this. And then here is a true lag and the inferred distribution for G and R band lag, right? That's good. And this takes about like 10 seconds to run. And how do we do this? Do supermassive black hole binary searches with EZTIS. And the solution is we introduce a new kernel on top of this right noise kernel. So we jointly fit in the right noise part and the periodic part, which is similar to other field, but we're doing it in a very fast way, so you can scale to large data sets. Here again, a demonstration showing the PSD of DRW. We show the red noise light curve. Here it uses the Lorentzian kernel. The Lorentzian kernel, by changing one of the parameters, you can actually change how coherent your light curve is. Example shows here if the quality is 200, you look very sinusoidal, right? Like you expect from Doppler thing. If you kind of lower the quality factor, it gets more quasi-periodic, more, as I said, flexible in terms of capturing different kind of or different shapes in the periodic variability. Okay, just to note, we're not doing actual Fourier transforms of the light curves to get the PSDs or do any kind of inference. We are directly fitting the light curves. Here, I'm showing the PSD just for a quick illustration. And we first started to test on some simulated light curve that has this kind of characteristic shapes of periodicity, starting with the sinusoid. Here in black dashed lines, it shows the input sinusoid light curve, and color ones shows the with the DRW added on top and downsample to the WFSC cadence, and on the right shows the inferred PSDs of DRW components and the Lorentzian components, where the DRW is shown in blue and the Lorentzian is shown in orange, and the black line shows those, and the vertical lines give the input periods, and you can see that the recovered, I said the best fit period of the Lorentzian, or here omega frequency, well matches the input, right? And we test on more complicated shapes of the periodicity is sawtooth pattern, which could be driven due to accretion modulation, or we've seen in not eccentric orbits. So for Doppler boosting. Also, again, you can see that this the input period and the recovered period is a match pretty well. Lastly, we tested on this flares, which could be due to gravitational lengthening of the emission from one of the black holes. So this is a little bit harder, I have to admit. Here you see this, the input has those flares, and right shows, again, the recovered, the PSD, the two different components. You can see we missed the period. But it actually makes sense that we miss it, because if you look at the cadence of WFST, you don't recover those, right? This gives you a wrong, the data give you a wrong period. It's not the method that actually fails. Okay, this is all, idealistic simulations. Then we tested on the beautiful light curves generated, which started from physical models, which gives more, results will be more important, right? And the way we do this is we fit two models. One is the pure DRW, assuming it's a single quasar variability with no boundary involved, and then we fit another one, assuming there's both accretion disk variability and some periodicity due to binary. And then we'll compare, doing this Bayesian way, to compare the evidence you get from this null model and compare the evidence you get from the alternative model. right? And then you use log B to select the best, the potential candidates. So the first thing we've done is, fitting these two models and see if their distributions have kind of diverged, right? If they have same distribution, there's no way you can make a cut of this and select candidates, which does show that for if you have only one noise, it's piled up at one part of the log B, and then if you have signal in there, a lot of actually extends to higher log B, which you can actually use log B to make a cut. This is single band on I band only, and the same for GRI band, which is where I think ExoTel X, the power of ExoTel X comes in, because it combines data from all different bands, right? This demonstrates that we can do multi-band, searches for periodicity in agent records. And how to actually, quantify the success rate, right? So basically, we'll plot the distribution of the log B for all the noise-only light curves and see their distribution. This is very simplistic. I'm trying to make a cut at a false positive rate of 0.005, which is like 0.5% for both I band only and GRI band. And then we choose those log Bs to select as a cut to select the potential binaries. And here it shows the results as function of the amplitude of the signal versus the sigma of the DRW. And here blue shows the single band. This is basically, I would say, comparable to others' results, right? If you have your periodicity amplitude is comparable to DRW, you get like about 20% of success rate. And as it goes up, because the amplitude of your periodic signal is stronger, then you get better chances of selecting them, right? Because it's stronger. But like what's exciting to me is if you look at the multi-band, it greatly, substantially increases the success rate of acquiring the true candidates, right? At about the comparable amplitude to the signal and the noise, you get like 70% of success rate, which is you cannot get with only single band data. Okay, just quick takeaways where developing this method to do multi-band modeling of agent light curves, and we can search for quasars with quasi or periodic variability, and some preliminary applications to Eden's light curve tell us we need to do multi-band, and multi-band greatly improves our success chance. And lastly, we're having two new projects. This has been submitted to the AGN Science Collaboration Project Database. One is, as shown, with preliminary results. We're going to run our methods on light curves, signal by Eden and Maria and collaborators, and then we will apply this methods to Rubin data to look for give us promising candidates to max plan. Okay, thanks. That's all I want to say.
Questions?
For the presentation, it was very interesting for me about just was it? Oh yeah. What kind of supermassive black hole binary would you expect to find first?
Ooh, so I haven't done from Eden's Likers, she simulated binaries from a range of intrinsic physical parameters. I haven't done the analysis deep enough to understand which it has higher successful rate, and that's what we're going to do next, so we can tell which one we can find first. Thanks for the question. Yeah, I just got the multi-band data like 2 weeks ago. So,
like the population census, somebody doing population censuses for like binary black holes.
Yeah, I think that's what Eden's Liker was trying to do.
Thanks a lot for the talk. So the improvement, can you comment on which part of it is like temporal and which part of it is increased wavelength coverage?
Yeah, so my initial, guess, I can only make an educated guess, right, is when we combine it from multi-band and increase temporal is when you have more data points, always easier to select the true binaries. Two is when you have multiple data, because there is always, that's it. There is intrinsic correlations between the disk variability as function of wavelengths. Now we combine multiple bands, it better estimates the noise level, whereas a noise is not photometric noise, but noise due to accretion disk variability. So you can have the actual periodic signal stance.
So do you think it's primarily the number of epochs, like that would be the primary driver?
I don't know. Okay. Thank you. Good question. I should probably.
I think it's easy to test, right?
Huh?
I think it's easy to test if you just limit the number of observation in the signal.
Right. So another results I didn't show is, which sort of probably related to your comment, is we see the recovery rate changes a function of bands. That is both due to the relative amplitude of the periodic signal versus the noise, but also due to one thing we know is the different bands and different number of payments. The reason why I was only showing I band is because I band is the best among the single bands.
Thanks a lot.
Yeah, thank you.
Mori, do you have a question? Go ahead.
I just want to know, are you fitting the same model to all light curves? So if you have non-periodic signal, there is a lag, but there is any transfer function between the bands?
Yeah, I'm fitting the same model of all bands, all light curves. Unfortunately, we're from Eden's light curves, there's no lag. So it will be something that we refer to as before, how lag works. But I have my own simplistic simulation, which doesn't come from physical models. I see that I can simultaneously recover, let's say, select the periodic sources and correctly recover the lag. Let me show you here. This is in one of my backup slides. No. Yeah, so if you, doesn't show, but anyways, so here is the one I simulated with the sinusoid variability, and you see this also pops up as clearly, and then here is the input, I think is GR and GI lag, and the vertical line shows the input, and distribution should recover the posterior, and got both right. But yeah, we should probably do more sophisticated stuff like transfer function, but this is just delta function. Yeah.
Let's do the last one.
Thank you for the great talk. I do have a lot of questions. First of all, the multi-band movement is very exciting. Second, when you take in these light curves, often LSST, Rubin will generate MJDs within a same 24-hour period, like very frequent sub-day cadences. Do you, in average, those observations or those MJDs, or do you use all of them?
Well, this should be a question directly to Ian, but I can probably help answer it. Is no, we don't bin anything.
Did you have a question? I can make a quick comment.
Okay, thank you.
If you want, we can also provide the data from Lin et al., which is exactly the same that Lorenzo used. So you can have a apples to apples comparison with the periodogram and the Bayesian pattern.
Yeah, I will be happy to test that.
It's in that computer.
Oh, yeah.
Okay, so let's thank Bayesian again. And next we have a discussion on our plans for 22, led by Marcin.
Speaker is Zachary Stein, who is going to talk to us about continuum reverberation by quasars using NASA Atlas.
Thank you. Yeah, hi everyone. We haven't had the pleasure of chatting yet. My name is Zach. I'm a second-year PhD student at the Australian National University. Today, I'd like to chat a little bit about continuum reverberation. So there's already been a lot of good talks given this week that have talked about continuum reverberation So just kind of quickly refresh everyone's minds. You have a central X-ray corona that's varying, radiates the surrounding accretion disk. That accretion disk will then absorb that radiation and re-emit it at the local temperature. Because the inner disk is hotter than the outer disk, you see this response burst at lower wavelengths. And if you try to measure a time delay between two continuum bands, you can try and get an estimate of the disk size. So this technique has been applied very successfully in several very intensive studies of secret galaxies, with an example from the first storm campaign up there on the left. Kind of a universal issue that people have come across, or maybe not an issue, but the disk sizes are about 3 times larger than you traditionally expect from a Shakura synergic disk. And one of the potential reasons this could be is that you have contributing emission from a more distant source, broadline region, with a sort of mixing between this disk delay and a more distant VOR that's dependent on the fraction of the flux that comes from each. So you can kind of qualitatively see that sort of signature in the Balmer series and the Passion series, but how much these signatures are present in the lag spectra is by no means universal and differs from object to object. So one of the things you can turn to is looking at large sample studies instead. Here you have to necessarily exchange the really good data quality for a larger sample, and thus the lags are a little bit less robust, but you can see how they change on average. And one of the universal results from these sorts of studies is that this size problem appears to be anti-correlated with luminosity. So to probe this a little bit further, what we wanted to look at is a sample of 10,000 of the brightest UV optical AGN in the sky. So for comparison, that's the general SDSS distribution of quasars underneath there. And we do so with Atlas data. So for context, that's an example light curve. We use 2 filters, cyan and orange, which is roughly GNR and RNI, respectively. So one of the good things about this study is that we had a really high sample count, about an order of magnitude of the studies before us. So this means we get some really good sample statistics. And one of the other things that we kind of picked up on from the previous studies is that you would get a well-constrained lag for maybe a fraction of the candidate light curves that you have. And the rest of these light curve information would kind of just be thrown away. So we thought, what if instead of checking that out, you try to use that information still to infer what's happening at the population level. So I'm going to show a comparison on a simulated data set that's been calibrated to the real Atlas data. We use this as an example using Javelin, which is a Gaussian process MCMC algorithm. So we just, when I refer to stacking, it generally just means adding a log likelihood. So log likelihoods during an MCMC run. So we see the original application, we just apply to individual pairs. It's much too noisy to see what the real distribution is doing. If you make a significance cut, you inevitably bias the distribution to larger signals, which is not very helpful. We're trying to investigate a size problem. You make quality cuts based on correlation or variability. And this works well in simulated data, but these properties show a correlation with Eddington ratio and color in that data, which does affect the lags. So that kind of rules that out. You can stack the posterior estimates from the individual runs, and you can see that it now quite well traces the distribution, but the uncertainties are much too large to see small scale structure. Finally, if you're instead stacking the likelihood functions during the MCMC run, you get these nice constraints, and you can be a lot more certain about it. You might notice some sort of much more faded points. Javelin has a bit of an issue with dealing with multimodal posteriors, so I kind of blurred those out because they didn't converge very well. So what happens when we actually apply this to the real Atlas data? What I'm showing here is 10 bins set uniformly in rest-frame wavelength, and within each of those is 5 bins in luminosity. Because we're controlling for rest-frame wavelength in each one, we're essentially setting the position on the disk, and then the luminosity kind of directly infers the size. So the convenience of translated those into units of the expected time delay. And one of the things that we see is qualitatively, when you control for redshift, there's no longer an anti-correlation with luminosity. They kind of scale as expected. So what's the reason that all these previous studies have seen it? So if we take the average amplitude, the ratio of what we observe to what we expect from the previous plot, and we now plot it with wavelength, we can see the relation shown on screen, where roughly delays are lighter than you expect at longer wavelengths and get shorter again towards shorter wavelengths. because our filters are so close together, we're really good at probing discontinuities. But in other studies where they have much more separated filters, you kind of average out this effect, or if you use multiple filters themselves. So you just generally, because of your flux limited sample, where your redshift and your luminosity are inherently correlated, all your more luminous ones are probing the shorter wavelengths. The sort of non-monotonic structure there as well, so it gives us clues to where some of this delay signal may be coming from. And qualitatively, if we take a VLR model for the signal and we drag two Atlas filters through the redshift and take differences in time delays, you would end up with the plot on the left, just qualitatively. Now, I don't really see this as being in opposition to some of the work that's been done here about talking about whether inherently the disk size is larger than you expect, because this is only a differential estimate, so we're taking pairs of time delays. But what it does say is that it's quite common for AGN to have some level of contamination from the VLR signal. That's happening at the population level. We can explore this a little deeper when we bin by other parameters. So here is controlling for, on top of luminosity and redshift, Eddington ratio. The high Eddington ratio points put in blue, the low Eddington points in orange. You can kind of see that on average, the blue points sit higher than the orange. We're getting a bit more scattered than the previous lags because we're starting to lose some of these sample statistics, but on average, that is the behavior. We can play similar games with ion ratios, so it's the ion complex equivalent width relative to some low ionization of ion, whether it's H beta or magnesium 2, depending on the redshift range. And we see a very similar behavior, and realistically, that's not too surprising. People who are familiar with the eigenvector 1 sequence, this idea of a fundamental plane that describes most of the quasar spectra diversity, we kind of see when we look there, if you make a cut in ion ratios, you're also kind of making a cut in Eddington ratio. But again, because we can't divide our sample too many ways with this method, we can't start to tease out which of these effects is dominant. One of the other things that we explored is photometric color. So when you take your color distribution, you can see a redshift-dependent trend because different emission lines enter these filters and leave. But once you remove this trend, you're kind of left with a nice Gaussian of color with maybe a dust spreading tail. And if we look at this sort of core distribution, we can again split our sample. These bins are starting to really, particularly say in panel 10 there, we're starting to lose a lot of the sample count, so it gets a lot more noisy. But again, it kind of looks like the red points consistently sit on top of the gray and the blue with a sort of ordering that goes by color. And this kind of opens up a potentially exciting avenue of measuring extra galactic dust reddening laws in quasars. But there are a lot of other potential reasons why you could also get this dependence. One is that the continuum emission from the VLR is also redder than the intrinsic disk continuum. You can get it from having more of a slim disk source with higher Eddington ratios. We can also get it if you have radially dependent mass accretion rates from disk winds. So this is something that we're looking at more to try and tease out which of these it could possibly be by comparing the spectra. But for now, it's only a possibility. Speaking a little bit about disk winds, we also explore potential correlations with emission line outflows, carbon 4. If I direct your attention to the first two panels in this plot, it kind of looks like the high outflow winds. So the carbon 4 is blue shifted relative to the magnesium 2. And these systems, the lags are longer. But point to raise here is that the carbon 4 is inside the leading passband cyan. So you have this inherent anti-correlation between equivalent width and blue shift. The higher blue shift points have a weaker contribution from the VLR, and thus you'd expect a large difference between the two filters, because the first one has less of a more distant component. And you can kind of see that relation flips the moment you get outside of having carbon 4 sit directly in your filters, but it's really, really hard to tell with only one extra panel. One other explanation that we explored is that carbon 4 winds and also that our outflows are transient phenomena. So that may be preferentially selecting quasars with higher frequencies of valve absorption troughs. And we did tentatively find that having a valve absorption trough resulted in a longer lag, but the sample statistics are really, really low, so it's really, really hard to tell. So to summarize here and sort of connect to what the rest of the presentations have been at this meeting, I'm really big in favor of a joint approach to analyzing delays. I think that they complement the studies that have sort of been presented so far really, really well, in that if you do things jointly, you get to look at much more of the fine scale structure that could be there in a model agnostic way. So while it's really, really beneficial to have a physical model for things as an independent check, you really need this joint level analysis to try and get to a signal that you couldn't possibly constrain with a single light curve. Also, just I suppose flagging that there is some level of BLR continuum as a widespread phenomenon in the population. So whether this is a dominant or subdominant effect, that needs to be dealt with. We also sort of showed that these delays are a function of spectral parameters. So I think it's really, really important to also have, well, I suppose, time coincidence spectra. You don't need the same sort of BLR level frequencies to fit with reverberation mapping of the lines, but having an idea of which quasars are similar in terms of up to a spectral decomposition is quite important. So when we do this sort of bidding process and figure out how close they are to each other, it needs to be based on up-to-date information. If anyone has any questions, I'd be great to take them.
Are there questions?
So I lost what you were saying a little bit when you were talking about the carbon-4 emissions. So you were saying, can you just clarify, like, so when you see larger carbon-4 emission velocity, how that tracks with?
Sort of the interpretation I was kind of going with was because you have the carbon-4 emission in your cyan, the leading band, and we're tracking the difference in delay times. If your average radius that the leading band comes from is further out, then you expect a shorter delay. And because the carbon-4 blue shift is anti-correlated with the equivalent width, you get a smaller contribution from the more distant thing. So the average radius in the cyan band is then shorter, and the difference to the orange band becomes longer.
I see. Okay. Yeah.
Kind of interesting as well, with the interpretation goes the other way, when you flip it, having less carbon-4 blue shift winds, having longer lags, actually runs counter to the rest of the eigenvalue 1 sequence.
Okay. Yeah.
Yes, please.
Yeah, if I can correct on that, maybe. So one way to test that hypothesis would be to try bidding by carbon-4 equivalent width directly rather than by blue shift, right? So did you try doing that, or?
No.
Okay.
No.
That'd be interesting to see.
So the thing that we're looking at doing next is also comparing just reanalyzing the spectra for these objects in similar bins. You try and put more direct constraints on what contamination looks like.
Any other questions? We still have time for one more question. Well, if not, let's thank the speaker. And next speaker is going to be Janis Direct. Okay, right. He's going to talk to us about terrestrial high energy neutrino sources. In a minute. Yes.
All the
I'm full screen here. That's a minor language. Anyway, yes, I'll be telling you about high energy neutrino sources, and I'm sure a lot of people have heard that this might be blazars, but in fact, this is still a very much open question that we're trying to figure out. Now, this is kind of how we started with this whole business. So the first association of a high energy neutrino with a blazar was to this source, XSO 506. So on the top, you see the gamma ray light curve. At the bottom is sort of a neutrino light curve, not really. But
IceCube found that there is a high energy neutrino in the direction of this blazar during a very bright gamma flare. So then they went back into their data stream and tried to look for more neutrinos, and they found that there is an excess of neutrinos in 2015 of lower energy neutrinos, but when you look at the gamma ray light curves, there's actually nothing really going on there. Now, in the beginning, both events were used to calculate the significance of association, which was barely 3 sigma. And in fact, this is the best we have so far. Like every other association you might hear about, or anything on individual sources, is way below 3 sigma. The problem came from when actually people started to model the emission and try to figure out, how can you get this neutrinos, and you kind of see that you cannot really have it both ways. It's either gamma rays are coming with neutrinos or they don't, right? And there are actually arguments for both cases. And in fact, most theories would argue that in order to make this the high neutrino luminosity that you need for IceCube to detect anything, then you will have a dense enough open field that you will end up absorbing the gamma rays. So in fact, this is probably the likest, the most probable case, and others have found that in other sources in the direction of neutrinos, we've actually seen this sort of suppression of gamma rays, which you can see this is source 15.2, and the gamma ray light curve at the time of the neutrino arrival does show kind of things. On the other hand, others said that, well, IceCube localization uncertainty is so bad that you can have multiple sources in the view. And this is another source, PKS 0502, which is very nearby to the original source, and its light curve is on the bottom here. The top is TXS. And when you have this high energy neutrino, it is in fact coincident with the gamma ray flare in the original source, but nothing is going on in the nearby source. But the excess, which doesn't have any response for TXS, does come at the very bright flare for the distant source, right? So the relationship between neutrinos and gamma rays is complicated, to say the least, and we're still trying to figure that out. But we're very fortunate that blazars are very bright across the electromagnetic spectrum, so we don't have to stick to gamma rays. We can use other wavelengths. So we started looking at radio emission, and we're again fortunate because we have the Owens Valley Radio Observatory, which monitors 1,800 blazars roughly, with a cadence of about 3 days for almost 20 years now. So we have some very nice looking light curves that you can see here. And what we can do is move away from the just spatial association and actually go to the light curves and see what was happening in the source during the neutrino arrivals for a large now sample of sources. And as you can see in the few examples I have here, some of the neutrinos, which are with the blue lines, come on top of very bright radio flares, others not so much. So the time we did this, we had about 100 neutrinos to play with. And you get about a 2 sigma association if you take lookout square effect and other things. Now, we needed, since it was the first time we're actually doing this, not only we need to understand what that 2 sigma really meant. Of course, this is not particle physics. If it's not 5 sigma, we don't even talk about it, right? So we had to do a lot of simulations. And we simulated blazars, we simulated neutrinos, we simulated their light curves, and you can see some examples here. And then we try to do this cross correlation in different scenarios. And something that was very clear is when neutrinos come with bright radio flares, there should be a very clear signal, and we don't see that. Now there are a lot of different assumptions here, which some of them are kind of strong, but there is a deeper problem. There's one that comes from the neutrino data, and it's actually what the IceCube people call signalness. So signalness is the probability that a neutrino is not really visible, and it's just coming from the atmosphere. So in our best case scenarios, there is a 30 to 50% chance that the neutrino you have is not real. So the moment you introduce signalness into your simulations, you lose all signal. But nevertheless, we figured out that if you have a large enough sample, so go to 5,000 sources with a relatively good cadence, you don't actually have to do as good as over, and you accumulate, the same number of the neutrinos with the same rate as we did today, that you might actually have enough statistical power to say something. Unfortunately, such a survey doesn't exist, and we're going to have to wait for the large-scale experiments to come online in several years from now before we can actually do something about it. But as I've said, we have other wavelengths, and actually in the optical, as you're all very well aware, we do have all these large-scale surveys for it. Here, the problem was that we didn't actually have a sample that was big enough to work, so we had to make one. And this is work that was done by Buya, who's a graduate student at the University of Turku, and he basically combined all known blazars, which adds up to around roughly 8,000 sources, and then went into all the different databases for Atlas, CTF, and wherever you could find publicly available data, and just combined everything into light years that you can see over there. And we have basically light years for about 5,000 blazars, which are looking pretty good. And then Alessandro Pazzi, who used to be a photo working here when they got all the publicly available X-ray observations. Unfortunately, here we don't actually have that much of, what would you call a light curve. It's only for maybe a few tens to 100 of sources, but we do have some X-ray information for about 5,000. So then this is what the sky kind of looks like. So all the points you see there are blazars from catalog. The circles or ellipses are the uncertainty regions from IceCube. So this is what IceCube tells you. There is, a neutrino source somewhere there. So all the orange points are blazars within that uncertainty region. All the blue points are blazars that are outside. So we call those neutrino blazars, the orange point, but they're not really. So this time we had about 356 neutrinos, so a lot more and a lot more blazars, but we still get about a 2 sigma correlation. Now, here we run into a different problem. So again, as you're very well aware, optical light years have gaps. And for some cosmic conspiracy, this large, significant fraction of neutrinos was coming in gaps. And there we don't have any information, right? We don't know what the source was doing, so this is not anything we can use in our analysis. So we're going to need a lot more blazars and a lot more neutrinos than what we were hoping for the radio stuff in order to do this in the optical. But again, LSST is here to solve this, and easily we're going to get a lot more numbers. The problem here is that LSST will not play well with ice. And the reason is because you need Earth to shield you from the atmosphere. But there is hope, because there is in fact now a neutrino telescope in the northern hemisphere, it's called Crete. It's in the Mediterranean Sea somewhere. It's not fully built yet, but there is already a data stream. There is already starting to get results, and most importantly, they're already starting to break records. This is basically one event that was discussed a lot recently, which was had a 220 PV energy. This is basically an order of magnitude higher energy than whatever IceCube ever got. And the circles you see there, that's the localization uncertainty, which it's about 3 degrees in this case. So all the different sources you see are in fact blazars there. But when the telescope is going to be in full built and operating normally, the expected uncertainty would be 0.1 degrees. So you have to shrink that down by a lot, and then there will not be as many blazars in. So there is a lot of synergies here between Chemtranet and LSST. And for Chemtranet, at least the data are behind some particle physics wall, but the alerts are going to be public. So I'll just leave you here with my summary, and thank you very much. Any questions?
Hi, thanks for the talk. So at the beginning you show the neutrino emission and the gamma ray in Fermilab, right? I was wondering, do you expect it to happen at the same time, gamma ray and emission?
Yeah. So basically, in the basic model you're gonna have a photon interacting with a proton. That will create pions, then some of them will decay to gamma rays and neutrinos. So that's why this was sort of like, picked up as a clear smoking gun, because you have gamma rays, you have neutrino. This is all sort of, there's a whole bunch of other problems with that, but this would be a straight, like the simplest model would give you gamma rays and neutrinos.
Okay, no, because I was wondering if maybe there would be like different emission region in gamma and neutrino, like in the jet, and maybe there could be some delay between the emissions. So,
there could be some delay, but again, in this case, you have years of nothing happening. So it's, like I said, this is a lot more complicated, and we don't really. If people tell you they know what is happening, they're
Thank you. I'm still so confused about processing, producing neutrinos and associations with other bands. And I mean, some people are claiming that the fact that the low energy emission radio optical come from silicon radiation, while high energy emission, if it must produce neutrino come from other processes. This difference in mechanisms can explain the fact that sometimes you see gamma ray flares without optical counterparts, and vice versa, optical flares without high energy gamma ray counterparts. You are looking for events coincident with the neutrino arrival. So are you claiming that even if radio and optical emission comes from a different process with respect to the one producing neutrinos, there is something that in any case link the two different mechanisms? I don't know if I
No, again, I have the point.
explaining myself.
First of all, let me say that the null hypothesis is always that you have the neutrino coming with the flare, right? Now, as soon as you try to introduce delay in your model, as was suggested, then basically your trials go, will grow exponentially, and then anything, it will not be significant. So you need a hypothesis that's clear, that can be tested. And this is an issue. And this is what I was saying for the simulations, that there's a lot of assumptions that go in here that might not be as a clear-cut case. But one of the ideas for starting with radio is because radio has, say, the benefit that sort of traces the underlying jet power. And it's usually much slower than anything else. Right? These flares last sort of for years when you have this slow rise. So the initial idea was, instead of trying to actually catch the peak of the flare, we can try to catch sort of the overall, power, the underlying power in the jets somehow. And as I said, that didn't really work out. That's why I moved to optical. Optical, we're trying for the the optical flare, which is much faster. But that doesn't seem to work either. So we're still trying to figure it out.
Any other questions? Yes, please.
Why do you prefer lasers? I guess everybody prefers lasers. Neutrino both come from the astrophysical source, but what about like long GRBs? Are they still too short for this kind of neutrino?
So this is again another very interesting source class, because again, all the theoretical models would suggest they would be making neutrinos, and in different energies too. Like there's like plenty of ways you can make neutrinos and GRBs, but any search from ice field has not found a single one. Even the people were hoping with the brightest GRB of all time. If that doesn't make neutrinos, what would? There's still zero evidence for any neutrino coming. Okay, so we have time for one more question.
So you mentioned the signalness of the neutrinos, and presumably the signalness is different from like cascade events and muon tracks,
Yes.
right? So what if you focus on the muon tracks, which are better localized and much more significant? Can you?
Well,
is it easier to pull out the signal?
It's the opposite. So the cascade ones are much more have higher signalness because they deposit a lot more energy. So they are much more certain that these were real, but then the localization uncertainty of those things is terrible. So the tracks are not as, they need to be high enough energy to have a high signal. But so it's they're working against each other, basically. Okay, let's thank the speaker. And next will be who's going to talk to us about LSST and LSST.
Okay, thank you. I'm Chang. I'm a postdoc at the Black Hole Initiative. I want to thank the organizer for inviting me to this amazing conference. I started astronomy being Maria's little summer intern at California, but she was a postdoc. I'm still working on the same stuff, so it's big fan. So today I'm going to talk about LSST and LSST energy in order to detect compact massive black hole binaries. But the real title is yet again another geology research. So there's 10 people in at least 10 people that should be asking questions. Right. So if you believe all quasars are caused by galaxy mergers, and so some quasars can be associated with a supermassive black hole binary that emits some sort of a periodic signature in the middle, we should know that we can predict these population of binaries by first predicting the number of density of quasars in LSST. So I did this work a few years back, and it's very exciting to see the recent agile results. So we took a very different approach. I started with observed quasar luminosity function, and I extrapolated to the faint end and high redshift. As you can see, the yellow covers where the quasar data were, and in the last two bins, there were pretty much no data, so it's purely depending on extrapolation of the quasar luminosity function. But we actually get that up to redshift, up to redshift of 6, and to a single magnitude limit, we get 20 million quasar, which is actually pretty consistent with the agile results with a factor of a few difference. So this is very promising. But we're all about precision, so I actually talked to Aker about this yesterday, and we're going to figure out the difference, even though our methods are wildly different. So this will be our little side quest that came out of this conference. But I want to address another thing, which is since most of the quasars are on the fainter end, we have a very steep faint end. Lots of quasars are low mass sources. So what does this mean? So this means what the time domain survey that we cover when we select the binary candidates from covers mostly up to the first 6 panels. But we would have a lot more in the era of LSST. And I'll show you in the next slide why these low mass sources are associated with short period binaries. So on the left-hand side plot is basically the same thing as the luminosity function, but as a function of black hole mass and redshift instead. And you can see in the darker side of the contour, these are mostly where the highest number density are in LSST. So these are around, it peaks roughly around redshift of 2 and black hole mass of 5 or 6. So a lot of these can, not a lot, but actually very few of these can eventually evolve into the LISA band and emit gravitational wave in millihertz range. But some of these can also be in between the millihertz and 58 nanohertz, so a period of a few months. And the lower mass you have sort of, if a binary has a lower mass, and if you sample all binaries and their time to merger on a linear scale over cosmic time, you get that the period of the lower mass sources are actually expected to be a lot shorter than the higher mass black holes. And this is because the lower mass sources chirp more slowly in the gravitational wave driven regime. So under the same assumption of time to merger, you have more time to catch the lower mass sources than the higher mass sources. And on the right hand side plot, I'm plotting the orbital period for two black hole masses, 10 to the 5, which is the bottom one, and 10 to the 8, which is the top one, as a function of time to merger, and this is exactly what you see. So the lesson here is with LSST that we should be seeing a lot of these very interesting low mass and short period. In terms of LISA, these would be the faintest sources with the shortest periods, and most of the periods would be within a week long. And we know the gravitational wave chirp, which determines the in-spiral, the binary in-spiral at the late stage, is determined by the chirp mass and the rest gravitational wave frequency. Also, sorry, the first F plot should be the orbital chirp, the ENM chirp. But we know from GR that in this stage of in-spiral, the orbital frequency is roughly half the gravitational wave frequency. So we could also get their chirp when they're in the LSST regime based on this formulation. If we use this simple assumption that the fraction of binaries at a certain time to merger is proportional to Tm over the entire duty cycle of the quasar, we get this simple relation that the fraction of binaries you get is proportional to this very small fraction times whatever binary fraction you assume is associated with quasars. So in this work, we actually use 1, which gave us the upper limit on this number. So if you plug these numbers in, for example, if you assume the time to merger to be 15 years, which is the time we have during the LISA mission, or until the end of the LISA mission, we get there up to 100 LISA sources would already be in LSST for us to search for when LSST is starting to give us all these data release in the next 10 years. But there would be a lot more sources that are also chirping, but in between LISA and PTA. So in order to identify these chirp sources, so my method is slightly different from the previous method mentioned, because my aim is also to identify chirp on top of periodicity, because I'm interested in these short period sources. So you can't visually see here, but this source actually have a 30-day period, and time to merger is 50 years. So by the end of LSST, after 10 years, the orbital period will be shrinking by 0.75%. So you can't really visibly see it, here, but there is a chirp component here, and my task is to recover that. So I overlaid them from the walk, and this is the continuous signal that you get, but we all know there's also cadence, mesh error, that kind of stuff. So this is eventually the data you're dealing with. So the goal is to measure 7 parameters, 5 chirp parameters, and 2 damper and walk parameters. So I think people are familiar with damper and walk now, but I'll go over the 7 chirp parameters in later pages. But the most important parameters I'm studying here are the binary signal amplitude, which is A, frequency, and chirp, so F and F dot here. I'm using a full Bayesian approach to do this task. I also want to assess the confidence for which I can recover all of these parameters. And then I want to vary a few parameters like the signal to noise, the strength of the binary signal compared to damper and walk, and the period range at the chirp range to do a full completeness and to do a full complete study. And then I'll comment on the runtime later on, since we're dealing with large data sets. Right. So I actually designed a pretty complicated Bayesian approach to do this task, and this is because the prior we get from ENM observation is pretty wide. So if you assume the uncertainty on mass on log scale is plus or minus 1, based on this chirp formulation, your frequency uncertainty is actually plus or minus 40%, and on F delta it will be plus or minus 143%. For this type of chirp signal you get, if you take a Fourier transform, the likelihood is also significantly quasi-periodic. So to recover the full truth or full maximum likelihoods is actually a pretty complicated method. So if you're doing any research that would require this method, you can ask me afterwards. Right, but the goal is to recover these parameters, and I'm showing you an example posterior of the light curve that I showed you in the previous slide. So these are the three most important binary parameters that I'm looking at. So amplitude, chirp, and frequency. And I define my detection statistics to be how compact these contours are, namely this z-score parameter. So this is defined as the mean of the posterior over the standard deviation of the posterior. And if it's larger than 5 sigma, then I call it good, meaning that your mean is 5 times the standard deviation. And I also overplot the truth in triangle here to show you where the truths roughly are. But overall, you can do this for all 7 parameters. And obviously, I cannot show you for all of the LSST light curves. But here's an example. And the lesson to learn here is in this particular case, you can see every parameter is recovered pretty well. But in general, some of these parameters are coupled. For example, frequency and frequency dot are coupled based on gravitational wave in spiral. And from these, we know these are also determined by the chirp mass and the time to coalescence. So in turn, you could also measure these physical parameters by measuring these properties of the light curve, which I think is pretty cool. And another one associated with astrophysics is the binary amplitude. 2 minutes. Okay, there's also the binary amplitude, as we know that's associated with the flares you get from the disk. So there's a lot of information here. So I want to show you this completeness study, and then maybe another result. Always run out of time early. So I tried a few values for time to merger, ranging from 15 years to 10 to the 4 years. At the closest range, this is the Lisa binaries. And I'm plotting you in the gray contour here, the period versus so the period as function of redshift and mass. So as I mentioned, if you fix the time to merger, the period is shortest for on the lower mass end and longer on the higher mass end. So your gradient darkened to the right side. And on the right side, I'm showing you the z-score statistics on the amplitude, meaning how well you can detect the flare. And this entire domain is for a signal to noise, meaning the finite signal is 5 times the temperament was. I do want to quote 2 numbers for you. So first of all, the z-scores are all above 5 sigma, meaning at this signal to noise, everything is very well recovered. But I want to quote 2 numbers. One is the widest binary for which we can detect this amplitude confidently. And it would only require 2 cycles, actually, which has period of 5. So this source has period of 5 years. But if you want to recover more parameters like F and chirp, then you would need more cycles, like how we understand we need more cycles to distinguish binary signal and dampen and walk noise. So for this one, we need roughly 20 cycles to recover the chirp. Okay, so I think I'll skip this and directly go to the physical measurements. So by measuring F and F dot very well, you can also convert those to chirp mass and time to coalescence measurements. So here I'm showing you the dispersion on log scale on the y-axis for chirp mass and time to merger. So the -1 level shows you a 10% uncertainty for both of these parameters. And as you can see for most quasars in LSST, the uncertainty on chirp mass measurement is actually less than 10%, meaning that the worst you can get is plus or minus 10 to the 4 solar mass. And this is already a very, very big measurement compared to other ENM measurement of black hole mass. And for time to coalescence, we can on average you can also get this to within 10%, meaning that if you have a measurement before Lisa even flies, you can constrain the time to merger to within 5 years. And this is within the entire lifespan of Lisa. So if we actually identify a binary with chirp in LSST, there is hope to constrain the exact time to merger within this window. I feel like that's pretty cool. So this could be potentially another way of measuring these physical parameters, especially offering another way to measure black hole mass. So runtime I'll skip, it's reasonable to expand this to larger data set. I also, if I can get 1 more minute, I'm so sorry, mention one more thing, which is I do plan to apply this to real data, and I have got this famous data set from a renowned Greek astronomer. It's Maria. So I did try this, and I ran basically a similar simulation with a different injected period and signal to noise to see what kind of detection statistics I should use to detect binaries with different periods and signal loudness. And then I plotted some broad curves to show you that depending on the signal to noise and also your injected period, there's a sweet spot. For me, it's signal to noise of 5 and periodicity of 6 months, where your actually detection statistics is strongest. And for a smaller period, you have aliasing, and for a longer period, baseline is too short for detecting those long periods. And I can also recover the physical parameter within 10%. So I don't have time for anything else. So thank you for that.
Thank you. We have time for 1, 2 quick questions. If there are any, please go ahead.
So if LSST detect a short period of binary candidates and provide a list, and these are first, I mean, based on your analysis, these are maybe able to see some signal, but can it actually localize the position reasonably well?
Yeah, so it depends on it depends on a lot of things. So I think it mostly sensitivity depends on the luminosity distance of the source, black hole mass, and also weakly, I guess, depends on the mass ratio and the number of cycles that you get. So I think there's been a few papers that calculated this. So depending on all these parameters, it can be anything between a few square degrees to a few thousand square degrees. So this could cover a few thousand to a few hundreds of thousands of quasars. So pretty big areas.
So I was just checking, if I'm understanding correctly, Lisa is currently nominally expected to launch around 2035.
Yeah.
Right? And so Rubin will be actually sort of most of the way through its first 10-year survey, and they will be probably looking for new ways to operate Rubin in the coming decade after that. Do you have any suggestions as to good ways to operate Rubin that would make it highly complementary to this kind of science?
Yeah, so in this work, I'm proposing that you can find these sources before Lisa launches, but you can also do the other way around, which is if there's a gravitational wave detection, you can go back in the archive and look for ENM counterparts. So the benefit of doing that is you have the waveform already, so you can extrapolate back to LSST time domain and know exactly how the frequency should be changing over time. If the source is within the localization, then you would have, if it's Lisa source, then you would have hundreds of, if not thousands of cycles because the period is so short. So that's very beneficial for us.
Yeah, well, writing down like what exactly you would want Rubin to be doing in terms of point consistent links for this many times or whatever could be very helpful.
Yeah, yes, for sure.
Okay, so that's supposed to measure signals.
Yes.
Okay. Yeah, sure.
Yeah, pointing this huge field of view.
Yeah, it's
huge benefit.
Yeah.
Right. So let's thank speaker. Thank you. For today, and actually for the whole conference, is a remote talk by Peter with Brandt Marcus. He's going to talk to us about power spectra of quasars from CGN light fields.
Hi everyone, can you hear me?
Yes, we can. Thank you. Can
Nice.
see you.
Just share my screen real quick. Yeah, my camera isn't working. I don't know why. Let me try to reconnect real quick to see if I can fix my camera. Otherwise, I'll present without it.
I can make a few announcements in the meantime.
Oh, okay. Yes, please go ahead.
Meeting is being.
Because at 5, I will try to keep you out of the room again. I'll do the final announcements of the conference now. First of all, we've asked Niel to go to the physics department and give the physics colloquium today, and he kindly agreed after a long week of conference. So the physics department is far, so we cannot go there, but I'm happy to share the Zoom link if you didn't have enough, AGN. So joining all follow. The second thing is again because I was Yanis to take him up. I want to thank a few people before we leave. So first of all, I want to thank the Science Organizing Committee, so Meg, Niel, Matthew, and Marcin, who helped us put together this schedule and the interesting discussions we had. And I also want to thank the local organizing committee. So Yanis helped a lot with organizing the coffee breaks and the dinner we had yesterday. Meg helped with everything, making the website, and generally running everything smoothly. And of course, Loki, Nico, Lorenzo, and Beatrice helped us run everything smoothly. So please give them a round of applause. And thank you everyone for coming. It was a great pleasure to have you here. And hopefully we will have another one of these in the LISA era when we will have the real data.
And I guess we should say a big thank you to Maria, actually. Right.
He was connected to share.
Oh, hi. Yeah. Can you see my camera now?
Well, part of the reason is probably because it's pinned. So yeah, it's pinned. So,
You think it's better if I shut it off to present?
Can you share your screen?
Yeah.
Please go ahead.
In order to my cursor to appear, do I need to share the whole screen, or can I share like just my navigator?
Share the desktop and go full screen in your presentation.
Okay. Can you see my presentation?
Yes, please go to full screen mode.
Sorry?
Go to full screen mode. You will now see your slides and everything.
Okay. And do you see my cursor?
Yeah.
Okay, great.
Wait. Victor, we'll let you know that you have 2 minutes left, right?
So, 2 minutes?
No.
You have 2 minutes, I'll let you know.
Okay. So may I start?
Yes.
Okay. Hi, everyone. I'm Vitor. I work at the astronomy department from the Federal University of Rio Grande do Sul in Brazil. I'm going to talk here about the power spectra of 0.4 to 0.5 redshift quasars from ZTF light curves relations with black hole mass and accretion rate. This work supervised by Sventrupta Panda and Thaisa Storch-Bergman. So just a brief resume of the science scenario we are about to dive into here. So optical AGN variabilities generally were described as stochastic red noise processes on diverse timescales, yet a growing population of changing look AGN extremely variable quasars and candidate periodic sources reveals behavior that deviate from simple stationary variability models, right? AGN variability is commonly characterized by steep red noise power spectra and damped stochastic processes, making robust identification of non-stochastic behaviors such as periodicity or state transitions particularly challenging to work with. And some problems we have in AGN power spectra analysis are typically red noise dominated. They are red noise dominated. They have uneven cadence, and most important, a finite baseline can produce false periodicity in most cases. And as we know, Rubin scale requires statistical rigor. So all of this I just said is a huge problem for us. This is just a picture of our standard model of AGN. It's a little bit out of date, but you probably all know this. So let's talk about the photometry survey we chose. Of course, ZTF came out as an almost obvious choice here, right? It has great field of view. You can check here in the image, and here's the LSST for comparison. Here's the footprint. This one is specifically for the G band, but they are pretty similar to the 3 bands. And ZTF solves 2 of the main problems here. Have great cadence, 2 to 3 nights, and most important, we had a baseline of 8+ years, which solves the finite baseline we were talking about. Okay. And also we use spectroscopic data in our analysis. We get it from this Wu Sheng 2022 catalog, as themselves describe a catalog of quasar properties from SDSS DR16. Here you can see 3 histograms that are basically the 3 things in our title, right? You have the redshift distribution here, the black hole mass, and edge-tone ratio. You can see that we have 650,000 objects each on this catalog. Then let's talk about the cross match and auto filtering we did. Objects with signal to noise less than 10 were removed, just to keep great signal, right? Have so many objects, why not? We decided to initially focus on the redshift range between 0.4 and 0.5. I'll talk about it real soon. And then cross-match with ZTF data was performed using the force photometry service. Light curves with less than 100 observations were excluded. So the final sample had 2,262 objects. Here are the exact same plots, but just for the final sample after the filtering. Okay. So this sample was first selected to observe double sources. You can check Luis Sanchez's talk from this very same event if you want to. And this redshift interval allows us to still see the H-beta emission line, which is important to studying double peaks. Also, Benatti Gonçalves and this work show that for the redshift range of 0.25 to 0.75, the highest line contribution was magnesium 2 for the G band with about 4% contribution. And also significant contribution was found on the R band for H-beta and O3. This also applies to our sample. I'm going to show 2 examples of spectra in the next slides. Another important point here is that ZTF light curves are well known to have few points on the I band, right? That's due to engineering design decisions and survey strategies. You can check here if you want. So most of our light curves looks like this example here on the right. The I band is not here because the code just doesn't plot objects with less than 100 observations. Okay. So here is an example of the spectra of an object at redshift 0.4. You can see here we don't have many contributions from lines. We can see this is the G band. Sorry. Here in the R band of ZTF, we can see that H-beta and O3 emission lines I talked about. Okay. And this is another example of another spectra, that time for an object at redshift 0.5. And as you can see here in the G band, we can clearly check this magnesium 2 emission line that is about 4% contribution I talked about. So as I explained and showed to you here, for these reasons, from here on, we only use the G band. Okay. So the PSD analysis pipeline doesn't have anything particularly new. So we start with this light curve. This is a light curve that has been filtered, as I explained. Then we move the NaN values. We check if there are more than 1 observations per day. If yes, we bin there to average the observations of that day, and then go to normalizing the light curve. If that's not necessary, just go to normalizing the light curve. With the light curve normalized, we compute the PSD, the power spectra density, with the Lombus-Cargo function. This is an AstroPy function in Python that produces the power spectra density. And of course, the output is the computed for spectral density. So here's just an example. On the top graph, you can see the light curve for a G-band from an object of our sample, about a little bit more than 2,000 days baseline here. And right above the power spectral density of this object, you can see that for this large light curve, we have a frequency of about 3.3 to 3.5 here. So that's why it's so good to have a large baseline, okay? Then that was Panna's idea. We separed our sample into, yeah? Okay, we separate our sample into beams of mass. It's on the x-axis in here, and adjutant ratio, which is on the y-axis in here. As you can see, the adjutant ratio decreases in this direction, top to bottom, and the black hole mass increases in this direction, so left to right in here. So here are the beams for each object. Of course, these numbers are the number of beams. And then the idea here was to stack, and by stacking, I mean take the median of the objects from the same beam. The idea here was to stack those beams to check how the PSD behaves. Here you can see our first plot. Here is the stacked PSD for adjutant ratio beams. So basically, we stacked the whole line of adjutant ratios. Okay. Here you can see that the adjutant ratio decreases in this direction here. So it goes from in the legend from bottom to top. So it follows this color order, purple, red, green, yellow, blue. You can see here on the graph, if you follow this order, purple, red, green, yellow, blue, it's increasing. And for that, we can state stacked power decreases with increasing adjutant ratio. That's our first statement. Then here we have basically the same plot, but for the mass, the black hole mass beings, right? Here's a little bit harder to see, but if you follow the pattern in which the mass increases, that goes from top to bottom in this graph. So blue, yellow, red, and so on. And if you can see here, I hope you can. When the black hole mass increases here, the stacked power increases mildly, right? And of course, this brown source has only 18 points, 18 objects, therefore, and so it doesn't exactly follow this pattern during all our graph, right? So we can state for this analysis that stacked power mildly increases with increasing black hole mass. And then, yeah.
2 minutes, please.
Oh, okay. To be quick. Thank you so much. So let's talk about this red arrow in here. So it crosses diagonally these beams. That means we're going to stack the beams along this diagonal, okay? And we want to do this because from this work from Panda, which is a theoretical work, the peak temperature of the accretion disk from standard accretion disk theory. From here, you can see that the max temperature of the accretion disk is proportional to the mass accretion rate over black hole mass squared. But we know adjutant ratio is proportional to mass accretion rate over mass. So we can therefore use this relation. The max temperature of the disk is proportional to adjutant ratio over black hole mass. And then here we have the stacks for that diagonal. We can check here is on the legend is the value of this max temperature, And you can see that as it increases from top to bottom, the stacked power decreases here, right? So if you follow dark green, blue, gray, see it, the stacked power decreases with increasing max temperature. So that's just our key takeaways. I already said. Our plans on ongoing and future work are compare our current stacking with Vincenzo's Petreka ensemble PST pipeline. Of course, why not extend the whole analysis to the full redshift range and also analyze the R band and use STWX from Weisheng to test and constrain the break frequency. Thank you so much. These are just some analogies. Thank you for your time and attention. If you have any question, comments, critics, feel free to speak your thoughts. Thank you.
Are there any questions, please?
Hi. Thank you very much for the talk. I was interested in the plot in which you show the Eddington fraction as a function of the total mass.
Eddington ratio as a function of total mass. This one?
No, the scatter plot. I think one more back. Then maybe two. This one. Yeah. No.
This one. The mass beams.
Not this one.
Oh.
The
plot with
the red arrow going from top left
to
bottom.
Yeah, this one. Sorry.
No, you're good. I wanted to ask if there is an intuitive reason to see. I'm sorry if I missed this, but to understand why you have scatter points on the top right hand side and not so much scatter on the other side of the arrow. Like it looks like every mass has a minimum Eddington fraction, and then it scatters on the top. I don't know if I was able to express myself in that.
You mean that for a beam? Yeah, go ahead.
Scatter on the top right, but not on the bottom left.
On the top right, but not on the bottom left. So in each beam, the points in each beam.
Yes.
Oh. Okay. So mostly I do believe it is because they just follow this law for max temperature of the accretion rate. For example, if you check this bin with 64 objects, they do actually group in the left bottom, right? And the same can be affirmed for this 5. But yeah, this is pretty much the only one that shows this behavior. So I don't think they do group in the right top of the beam. I just think they kind of group along this diagonal, mostly because as the accretion disk theory says, the max temperature of this disk has to follow this proportion, right? That's why we state that the stacked power decreases with increasing Tmax. We tried this for a few objects before, and we actually saw these values from this ratio, right, converging instead of decreasing. So there might be something there. Yeah, that's a great question. Makes total sense. I hope
Victor, if I can quickly jump in there. So basically, this is a sample. This is why I'm here. By the way, the thing that you're not seeing in the bottom left, it's basically a selection effect from the SDSS. You're not really sampling a low number of objects or low masses. But Victor also has done this analysis on the other diagonals where you have a little bit more occupation fraction, those that you see a little bit more dark blue. And we see the same trend with the temperatures, but this is something ongoing. And we like to explore the whole parameter space when he analyzes both the G and R bands for the entire set of light curves. But yeah, that's something very interesting that we are looking into. Thanks.
Yeah, I think I do have the question, the plot for, yeah, here's the other diagonal, this top one.
Okay. Thank you very much for the answer.
Thank you, Panda.
Thank you very much. I don't think we have time for any more questions. So let's
Yeah.
thank all today, and let's go for cocktail.
Thank you so much.
Can I ask you something very quick? Or no. Okay. Very cool. I think I'm always happy to find your so in the last in the KM, not you show the object where it's the one that declared the more thing the right? The one that had issues with 5. Anyway.
No, there are a lot of people switched. Actually, this is one of the great examples of the basically just the solution is marine biology.